All right. Okay. I think we are now recording and we are online. So welcome, officially welcome to the 12th Gaia Science Alerts Workshop and the first Optical RadioNet Pilot time domain meeting. And my name is Łukasz Wyrzekowski. I've been bombarding you with all the emails about the preparations for this workshop. So I'm glad we are here partially in person, partially virtually, but I'm glad for this to begin. Before I go to technicalities, I will let our local host here, Vasilis, to say a few words, if you're there, Vasilis.
Yes, I'm there. Hello, everyone. I don't know if you can hear me. I presume you can, right?
Yeah, that's okay. Yeah.
I would like to welcome you again. I'm sorry I'm not in the room with the rest of the people because we had a faculty meeting here in the physics department. I had to be here, but I'll join you later in the afternoon and tomorrow. I would like to formally welcome you to the partially sunny Crete. The weather is likely better than what it is in Northern Europe, but unfortunately, due to the exciting program that Lucas has already set up, it may be that many of you will not, the ones that you are here will not be able to profit, but I'm sure that they will be able to do that at least partially on Wednesday when we'll go up to Skinnakas Observatory for a small tour for those who are interested. And I look forward, together with the rest of the people who are joining from a distance, to the exciting talks that have been scheduled, as well as the prospects that the Optical RadioNet pilot is offering to the European astronomy. And I'm sure many of you, including Jean-Gabriel, who is giving a talk, and Jerry later in the week, will talk about this. Okay. Welcome again, and Lucas will give you more details about practical issues.
Okay, thank you very much, Vasilis. We'll see you later, I hope, in person. Okay, so as I said, this is the 12th Gaia Science Alerts Workshop, and these are the posters of all the previous ones, and there will be slight delay. Apologies for this. Because of the technicalities we decided to go for, there will be half a second delay between what I say and what I show. So be patient. So we started in 2010 in Cambridge with funding from Crete, and then we moved on. We've been to Cambridge, Bologna, Paris, Warsaw, Liverpool, Utrecht, Warsaw again, Lipava, Catania. Then the last year was online actually, and we are now back on track with physical meetings in person, which I'm very happy about. And this is the first time we do it within the framework of Optical RadioNet pilot. Previous years we've been using funds from Opticon, generous funding, and now we moved on. Opticon merged with RadioNet. We'll hear more about it later, but the meetings we initiated 12 years ago, they still continue to be part of this, and I'm very happy about this. It means that we will have more meetings to come, so I'm looking forward to those as well. And we started with Crete, very nice destination, but we will probably travel to other nice destinations in next years. This is just, a promise that we'll continue doing this. The funding is secured, and as long as there's will to meet, we will continue doing this. So some technicalities for this workshop to work it out correctly, because this is the first time I'm doing a hybrid meeting like this. so I'm a bit nervous, but we will rely on well-tested tools like Zoom. And the main thing, please, on Zoom, please mute yourself when you're not speaking. That's the general rule. Then for questions, of course, we communicate via Zoom. You can raise your hand on Zoom. Even if you're present in this room, then please raise your hand on Zoom. You can type your question. This is quite convenient because you can type your question during the presentation, and then we will read it out, or you can read it out, right? So you don't have to wait until the very end, the question session. We have set up the Slack workspace within the Black Hole Tom workspace. There's a dedicated channel for the discussions, and it has a longish name, but all of you who registered, you got the invitation to this channel. I think you don't have to be even registered to this meeting to use the channel. So I hope there will be some informal or formal discussions about further discussions about topics we started discussing. I've also set up a Gather Town space for meeting the virtual attendees. Some of you are familiar with those. These are quite convenient tools when you walk around on a beach there, and you can meet other avatars and talk to them immediately. So I do recommend this. Here, for those who are here locally, we have a real beach and we have real bars. So we will do it here. But for the rest of people, I do recommend to use this. Not now, of course, don't do it now. Now, stay here. But for other times, please go and see there. We will also tweet. We'll try to keep up with the talks, what's going on under this hashtag GaiaPDA ORP 2021. For people in the room, a few additional notes. We will try that you will present your slides while, like if you were outside of this room, right? So we will start your screen sharing, your presentation from your own laptop. If you have problems with that, then let me know beforehand. We'll come up with something. And then the main thing is that keep yourself muted. I mean, not yourself, but the Zoom microphone mute and speakers off. That will help us avoid all the feedbacks. Because when we have the microphones, we have one microphone here, a central one, which collects the sound from everywhere. I will ask the speaker actually to move forward. This is where Laurent is sitting. This is the best spot to get your audio well transmitted. So when you're speaking, then you move here. We need to wear masks when not speaking. I'm not having my mask now, but generally that's the rule. We were kindly let into this room, but there are limitations and restrictions we should obey. So let's don't forget about this. For the Wi-Fi, there is only a room, from what I've been told. If you have problems with that, let me know. Right. And that's it, what I wanted to say. And I think if there are no immediate issues, I have to see the chat. Chat is here. Thank you, Simon, for feedback that you can hear me well. It means the microphone is working. Excellent. So I think we are ready to begin. I'll stop sharing my screen, and I will let Laurent speak about Gaia and Gaia Parabit.
Okay, I will share my screen. Then I can check. I'm here, I can check that everything is going well. Okay, so my name is Laurent Ayer, and I represent a significant group who are working on these variable sources of Gaia. And I will speak about the variable source of the Gaia third data release. But first, the typical slide I'm presenting about the Gaia mission. The Gaia mission in a nutshell. In fact, it is a survey time machine. It is a cornerstone mission of the European Space Agency. It is observing all objects brighter than a certain limit. It's about 2 billion objects. It's measuring position, brightness, colors, radial velocities. It was launched in December 2013, and the end is foreseen somewhere in 2025 if it is approved by ESA, if the extension is approved by ESA. Now it is formally approved to end of 2022. So for 10 years, if we take this basis, the whole sky will be measured on average 140 times in each of the 9 CCDs for the G-band, in the BP and RP CCDs, and about 80 times in radial velocity spectrometer. So why Gaia is so extraordinary? It is an optical measurement of the entire celestial sphere. Several instruments on one space platform are performing nearly simultaneous measurements. There is a very large dynamical range from magnitude 4 to magnitude 21 with uniformly calibrated photometry and astrometry, and also the spectroscopy. There is a very large number of sources, as mentioned, about 2 billion objects. It is multi-epoch. There is now, I think, about 2 trillion photometric measurements, so it's very large numbers to deal with. It is an exceptional astrometry, and with this exceptional astrometry, you have an unprecedented 2D map over the whole sky. Gaia is also giving depth to space with a parallax, and Gaia gives motions to stars as well. Gaia gives characteristics to stars, astrophysical parameters, variability, and binarity. It's a fully European project. And so this, I think we can say Gaia is a very unique mission. The focus on the iterative approach, so there was several data releases, and there are several others to come. And if we have a look for which concern the variability, globally, this is a very super or hyper trail, I don't know how to call it, but we had the first data release in 2016, and then you had the DR2 in April 2018, and now we will have, beginning next year, DR3. There is DR4 and DR5 to be planned as well. And if you look now at the number of stars we delivered, at the beginning we had the 3,000 stars that were published with a detailed photometric time series. In DR2 we had 500,000, and now we are reaching for DR3, there will be 11 million variable sources, and we hope to go even further. And there is also an increase of complexity along the different data releases. The data we take as input. In the DR1, we were using only the time series in the G-band. In DR2, we had the G-band, and we were using the BP and RP integrated time series. We were using also the astrometry and also the per CCD photometry in the G-band. For the DR3, we are using all other parameters, but now we are trying to exploit the radial velocities and also the RP and BP spectra time series. And then for the DR4 and DR5, we hope we will have all the information. And so the output of our processing, we see also there is an increase. Initially, there were 2 variability types in DR1, then 7 in DR2. Then we have now 25 variability types. And there, for DR4 and DR5, we will again increase this number of variable objects. Now, if we look on a global output of the DR3, so what is happening with respect of EDR3, there is an unchanged source list, unchanged astrometry, unchanged photometry. There will be BPRP mean spectra for about 100 million source, RVS measurements for 1 million source. There will be 30 million mean radial velocities. There will be a catalog, a variable star catalog, as I mentioned, of about 11 million sources. Some radial velocity time series will be published for 2,000 stars, for the RR-Lyrae and Cepheid stars. There will be also 100,000 non-single star catalog, astrophysical parameters for 500 million sources, a pencil beam of photometric time series in the direction of M31, and about 150,000 solar system bodies. So globally, across the entire consortium, there is this increase of diversity of products. Now, again, if you look at the different successive data release, globally, the more data you have, the more precise you are getting. At least that's a good target. So there is a lowering of the random errors. I remind that the photometry is going like 1 of the square root of the mission length, position and parallax the same, and for proper motion, because you are gaining from the time, you are going 1 over the mission length times the square root of the mission length. You have also better calibration, better data reductions. People are working, so you have lower systematic errors. You have a better source list and more diverse products, as I mentioned. Here is a little example with what is produced by the group, the CU5, Coordination Unit 5, coordinated by Cambridge. This is the photometry. You have the dependence of the photometry, the uncertainty of the mean as function of the mean G magnitude. So this was for DR1. You see here, you see the mouse, you have some, it's a bit difficult, you have features here, you have a little bump, and you see it's not so clean. It's already fantastic, but then DR2, it's improving, and DR3, you have improvement. So globally, the calibration, it's not only the question of increasing the number of measurements. This is really an improvement of the calibrations. Now, if you look at the variables here, we will prepare, in fact, these diagrams for the DR3. I could not show them now here, unfortunately, but there was this diagram of the fraction of variables across the HR diagram, which is showing that you have the instability strip here. So the fraction of variable is higher than other region. You have, for example, the ZZ clump here. You can remark it, and you have some things which are well known, like the redder you are and the brighter you are. You have 100% of the variables which are here, and also down there, if you are going away from the main sequence, you have a higher probability to be variable. And then, thanks to Gaia, these multi-epoch measurements, what is happening is that you can bring the HR diagram alive, and you have the different motions. Can we see them? Not yet. You have the different variability types that you can see, and you can plot the data, and really you see things which are moving slowly for the long period variables, the Myra, and it can be quite fast, for example, for the Delta Scuti stars, or a bit slower for Gamma Dorado stars. You have this here, I think, eclipsing binaries. And so you have a whole population. So obviously with the DR3, we will improve significantly this animation. Part of DR3, there is also this pencil beam. So in fact, that was proposed in 2019, and there was this proposal to do, in fact, to output all time series of Gaia for a certain region, so that the stars are constant or variable, and so that it's to prepare a bit the community to see what is the performance of the photometry Also probably some spurious effects. At a point, it was even thought that the astrometry will go out with this pencil beam. Unfortunately, it was not really possible. But I think that's a good step for the community suddenly to understand what is happening. So several fields were considered. Here are several. You have an overlay of the scanning law. And you see that, for example, Plateau fields or Kepler fields are in dull regions. So we thought about this, but it's not that good. But the Andromeda is a very interesting region with respect of the scanning law, because there is a very diverse scanning law. And so that's exactly what I said, very diversity of the scanning law. There is a good description of Andromeda itself, as we will see, enough foreground stars to have a nice HR diagram with an opening of 5.5 degrees. Also, Andromeda is a well-known object. It was surveyed by different instruments, and globally there is an output of 1.2 million sources with opening of the cone of 5.5 degrees. The name that I didn't give it, but that's GAPS, Gaia Andromeda Photometric Survey. So here is a sky plot, a close-up of the sky. It's taking a bit of time to appear. So you have the Andromeda galaxy, it's very nice. You have M110, you have M32, the G1. So it's quite a nice, Gaia there gives a nice picture. So obviously you will have crowding regions, which will be more perturbed. And there, this is the number of field of view transit that there is. So you see there is some pattern. We could see that there was a region where you have many measurements. And also you see that the Andromeda itself has a lower number of measurements. This is probably due to crowding. If you do a color magnitude diagram, what do you see? You have several features, and there you can extract what is in the foreground in this. So you have a beautiful HR diagram. It is like Hipparcos, size of Hipparcos. You have also the white dwarfs, very nice. In the back, you can try to select, in fact, the stars by the trick that was used by Xavier Loury in the paper on LMC. You have here that's proper motion, and you see there is a clump. It's probably the background stars there. And you select these, and boom, you do the diagram, HR diagram for these stars. And what do you see? Okay, you have kind of clump. Is it the red clump? So you have some feature in the halo at 60 kiloparsec. So I asked Vassily Belokurov about this, and he said yes. There might be the halo is complex, and there might be some clumps. He gave these two references, in fact. Now, what processing do we do? Globally, we do supervised classification. And so we have 1.8 billion source at the entrance. You have 365 billion photometric measurements in G-band. Then you have the BP and the RP at the level of 46, 48 billion, and you have the RVS, which is at the level of 500 million. And then we compute parameters on these sources, and then we try to separate variables from non-variable objects. And for then the variable, we look for some modeling. It can be with a period search, with a Fourier series, for example. And then we have this general supervised classification, which is spreading in 25 types. So obviously what we need is, as it's supervised classification, we need a training set. And then we had a huge effort on assembling catalogs. The Gaia Science Alert is one of the catalogs that is included in our more than 150 catalogs. We assembled 8 million sources. There are about 100 types, subtypes. And globally, the cross-match was based on positional and magnitude difference. The training set for the general variability detection is made of two types, variable and non-variable, or other. And so that's 60,000 variables and 63,000 others. And then the training set for general classification, there is 40 type groups. For example, I think there is a kind of group of constant stars also. We reproduced this. So we have the constant stars in a way appearing from here and also from here. And then we have 24 variability types, stellar variability types, and we have one type of that are galaxies, in fact. I think I will speak a bit later about this. And then we used the classification framework called H2O. We used XGBoost and random forest, distributed random forest mostly. And then some statistics. So we have 14 million sources. There is 1.2 million objects in GAPS, this photometric survey. There is about 2.5 million galaxies. In fact, the point is that galaxy, we don't claim galaxies are variable, but they are variable in the reduction of Gaia. So from a spurious effect, we get we can detect the galaxies. It's what I'm using, and we have about 11 million objects. So if we look at the distribution of these objects, globally we have eclipsing systems, we have pulsating stars, we have rotation-induced variability, so that's globally the major types. So now we will go through a few light curves. So this is, for example, an arc coronae borealis. You have the time as function of the magnitude. You have a drop here of 6 magnitude. It's very impressive object. We have, it was classified as supernova, which was not in the science alert because it was during the beginning of the mission. So we had this rise and then these few points later. And so when you look where the object is, it is in a galaxy. So there is a high chance indeed it's a supernova. We have the microlensing events. That's the work done by people here in the room, Katarzyna and Łukasz. And also there is this very beautiful image of the week, work by Chris Rybicki and Łukasz and Katarzyna. But these, where we merge astrometry with the photometry, won't be in the DR3. That will be for later. There is a long period variables, so now we start to have several cycles even for the very long period variables. Also, we are using the RP spectra to distinguish between carbon-rich and oxygen-rich LP, so there will be a sub-classification there. So suddenly we are making use of these RP spectra. There is also AGN QSO. Here is a little example. We provide in the catalog that will be, so in DR3, the parameters from the structure function. There will be eclipsing binaries. There will be also exoplanetary candidates. So one was discovered. This is the first exoplanet detected by Gaia. It was an image of the week already many months ago. And this one was confirmed. So we did follow up on the candidates we had, and there was this one which was good. Then we have also white dwarfs. There is also a parallel study done with the DR2 where we look at the white dwarf variability, and it will be interesting to compare. But again, we see a very good big clump, probably of ZZ Ceti stars, then an extension at the V777 Hercules stars, and that's GW Virginis stars probably. So we are able to detect them as well. We have also the Cepheids. There, the Cepheid, you have the G band. the G band, the B band, and the R band, and also the radial velocities time series here. You have many of them also for the RR rays. So globally, there will be about 2,000 Cepheden RR rays. So that's again the same description where we have the BP, the G, RP, and the radial velocity. So this is beautiful. The data set is in such a way is, I think, does not have any precedent. And you can do things like period luminosity of RR Lyrae stars. This was with Hipparcos, what could be achieved with Hipparcos, with the DR1, DR2, and now with DR3, EDR3. You see that you have the beautiful period luminosity relation. This is appearing in the infrared band. For RR Lyrae, you have also beautiful plots like period and peak-to-peak amplitude. So you start to see really, again, this is unprecedented description. Here you have the RR AB type, the Bailey's AB type, here the C type. And then you can do many different things. So if you look at this plot, where you have the color, the apparent magnitude versus color for these candidate of about 270,000 stars, you see this strange a bit vertical line. You have this diagonal, and so you have different clumps here. And obviously they are, we can understand easily. You have on the right a map of the Milky Way or the entire sky with the Milky Way, the SMC and LMC. And here you have the LMC, which is appearing as the big clump in the diagram. You have the SMC, smaller clump, fainter. Obviously, SMC is further away. You can take the Sagittarius dwarf, which is nearer there. It's the black, little black thing here, and you have it here. And you can also take the bulge, and that's the extinction, which is creating this branch on the side. Obviously, you have extinction. And you can also see, for example, Sculptor, which is quite far away. This is this little clump. So globally, this I did with TopCat is very easy. You select the region of the Sculptor and you map it in the color magnitude, apparent magnitude diagram. And then I will finish by showing this little animation that several of you saw it. Obviously, it's with the zoom, it's a bit not very continuous. And so you have an image of the Milky Way there and the SMC. And then you have, we are going away, we put the distance of the RR Lyrae, and you can see the little streak here are globular clusters, and you see here the branch. We don't see it so well. You have the branch of the Sagittarius stream. So this is it's a very beautiful diagram where it's very clear. You see the Sagittarius stream, Sagittarius galaxy. So in summary, so by essence and design, Gaia is a time domain machine. Gaia brings motion to astronomy in an unprecedented way, and it brings a lot, especially for variable stars. Gaia, I think, is a really amazing project, and I'm very happy to have spent so many years on it. And so this is, thank you for your attention.
Thank you very much. Excellent. Thank you, Laurent. We have one question on chat already. Pavel, you can start.
Yeah, well, thank you, Laurent, for your presentation. I hope all of you hear me well. I mean, the Zoom people, right? My question is about the bound on the magnitude, the uncertainty of the magnitude versus the G, mean G magnitude. There is a bound around 11, 12 G magnitude. What is the reason?
Yes, so you have several on these, maybe I can. So in order to have a large dynamical range, Gaia needed to integrate only a part of the CCD. So you have a gating system on the CCD. And so that means there you get into more problems calibrating those gates. Furthermore, you have a series of bumps. If you look correctly, you have also the way you have the windowing scheme are changing. And at the change when it's in a way, when it's entering a certain magnitude, you have a certain windowing scheme. When it's detected as lower magnitude, you have another one. So you have to calibrate those things. And we see that globally these effects, they are corrected very significantly from one data release to the other. That means the people who are doing this calibration, they understand these effects and they take into account. Obviously, it's not going in one go. And so there you can expect things will still be improved. So globally, you have a windowing scheme change and also gating system. And obviously, at brighter, you have the effect of saturation. Sure.
Thanks.
There's another question on chat. Ashish, I hope you don't mind. I'll take it over from you because I also wanted to ask this. Ashish is asking about the vertical and diagonal lines on the RLI map. Are they due to some selection effects as they seem too perfectly sloped? And I think this is the effect of blending, right? And so because there is this effect in along the line of sight, the distribution of RLI, which is not physical, right? But it remains there, so there is no way to correct it.
So it depends on which lines. I have the plot here. Thank you. You have this little streak here.
Yeah. Yeah.
So this is simply because there, I think there is
in Zoom. I don't think we are seeing the right slide. By the way,
it's the right slide. Yeah. It's the.
It's not the right slide. Which slide?
Okay.
This.
Any one of those, yeah. But I think you were on the wrong one when maybe it was just the time delay, perhaps.
So because there in this one you have this obviously for you derive the distance through modulus distance there, and I applied a very simple rule in optical that the RRAs have a fixed magnitude, and obviously you have an uncertainty, and poof, you are doing a little streak. You should distinguish also there you have the streaks in LMC or galactic center. This is because there the extinction was not corrected. Mm-hmm. So my goal is when we have the data release, that will be corrected. So yes. So there are these two effects. There is the effect of extinction, which is not corrected. And the other is simply you have uncertainty on the maybe too rough estimate. If I remember well, we chose we chose the RRAB, so that's also already reducing things, I think.
But you derive distances to each individual star separately, right?
Yeah.
If you kind of treated it as a system.
Yes, sure.
Yeah.
Yes.
Then that would probably solve some.
Yes. But for example, at École Polytechnique, they developed virtual images. So you put the virtual reality, and you put, and so I plotted this, and I asked the person, Florian Cabot, to put the known objects and to see if it's fitting or not. And sometimes you see strange things. I think I spent 1 hour looking globular cluster after globular cluster and trying to identify. So sometimes the distance are wrong. So you know that distance in the literature are very wrong. Sometimes you have two structures. I remember once I could see two structures, different structure in Gaia, and apparently there is one. So I need to explore a bit the literature there.
Okay, that's pretty cool. I wanted to ask one question. So you showed the equations for the improvements with the duration of the mission, but this does not necessarily apply to astrometric time series accuracy. because there is this ageist solution, right? But my feeling, and but maybe that's why I'm asking you, is there is also going to be an improvement of per epoch astrometric accuracy if you have a longer mission, right? Is this right?
I think because you will improve the calibration. So for example, currently the astrometric solution does not take into account color variation of the source. And so there is a list, the people working on the astrometric solution, they have a list of improvement. They know where to go, what to do. And so the question is when they will do such improvement. I was hoping that, for example, this color correction of the astrometric solution, so that they take into account the chromatic corrections, that I was hoping it was for DR3, but it won't be for DR3, it would be for later. Yes. So globally, the per epoch photometry will gain from time. It's like we see that in the photometry as well. That globally the things are
per epoch improves.
Per epoch it improves.
Okay. Perfect. Are there any more questions here from the room?
Yes, I posted that question. I think from 38 to 40 slides, can you show us one of the 38 or 40? Yeah, slide number. Yes.
Yes, I should.
Yes.
30.
I think it's, yeah. You see, there is scattering near 0.5 period. It's a little more scattering. And if you look in 39, it looks like it's the same. It's more scattering around that number, and 40 is the same. Do you know why? It looks like there is some kind of pattern maybe, or is just...
yes, I don't know. I would have to. You say where? Here?
Yeah, 0.5.
0.5.
Yes, yeah.
It's better visible.
Okay.
Yeah, it's better visible, but it seems like there is some kind of pattern or...
Yeah, maybe there is something happening there, because you know that you have these, for example, this Hertzsprung progression. The light curve is a bit modified according to the period. So maybe there is something that might be something interesting to explore. The point here, that this diagram, if I'm not mistaken, is done still with a DR2 source list. So globally, this diagram will contain even more points,
okay.
I think.
Okay, thank you, Laurent. So let's move on to our second speaker. And now we will have a virtual presence of Simon Hodgkin from Cambridge, who's going to tell us about Gaia Science Alerts. Simon, are you with us?
Hello, can you hear me?
Yeah, we do. We can hear you and we see your slides.
Do you see my screen?
Yes.
And that works in full screen, it looks okay, does it?
Yeah, that's fine.
Fantastic. I'm very happy to be here, but I really wish I was there. So I will sit here on my own in the cold and think about your lunches. And meanwhile, I will tell you about what we're doing with the Gaia Science Alerts. And as I was writing this, I realized we've been running for 7 years now. This is quite a significant contribution to the transient surveys that are existing. I think we've got a while to go before we catch up to Catalina, but I'm glad that we've been able to keep this operating for 7 years, more or less continuously. So a lot of what I'm going to talk about is in the paper that was published in May this year and is available in ANA. So I put that there. And when you see the slides, you can follow the links and get at the paper and that kind of thing. So if I go over things too quickly, go and look in the paper or ask questions. So for people who are not familiar with the Gaia Science Alerts thing, we basically have two kinds of event that we're looking for. And for both these kinds, we need them to be seen in two Gaia fields of view. We need to see them twice. So the first thing is a source that is new to Gaia. It doesn't exist in our giant database of all the measurements Gaia's ever made. It's a new source. And things you can imagine, supernovae, novae, dwarf novae, tidal disruption events, those kind of classes of source that we didn't previously see. And we need them to be brighter than 19th magnitude at least once in one of those fields of views. And then the other class of event, and where maybe we're a little bit different to many of the other transient surveys that are operating, we look for things that change brightness statistically significantly. So they change either by a magnitude, or for a particularly quiet source, we allow it to change by a smaller amount. And that increases our sensitivity to low amplitude microlensing events, for example. Or we have another detector, which is for slowly varying sources. So sources that persistently increase or decrease over long time scales in brightness. So hopefully with that, we cover most of the classes of transients or essentially one-off variables, things that are not the kind of things Laurent was just speaking so nicely about. We try to avoid the periodic variables. Better to wait for the formal Gaia data releases for those. What we want to publish are things that are important to study now and quickly, where classification of the event could lead to more follow-up photometry because the Gaia cadence is not so good. And as we see with the microlensing events, it's very important to get very good ground-based photometry quickly. Then when ultimately the Gaia astrometry becomes publicly released, the two will prove very powerful together. But if we didn't trigger the alert at the time, then that information wouldn't be collected and would be lost. So the thing to think about with Gaia is very different to most of the transient surveys that operate where you get a picture of the sky. We don't have that. We are a catalog transient survey. And the sky to Gaia, the two examples on the left are a bit exaggerated. These are worst case scenarios, having a bright planet in the field of view or a very bright star in the field of view gives us a lot of artifacts on board. And so we're always working with catalogs that even though a lot of artifact classification is done and it's minimized, that doesn't mean we don't still see the leftovers because no classification is perfect. So for us, the sky is quite noisy and full of, especially near bright things. And we can see the spikes of Sirius several degrees away. Even when the source is outside the field of view, we're still impacted by these bright star artifacts. And so the right-hand side is just zoom in on a few arc seconds by a few arc seconds. And it shows the problem of the initial data treatment, where there's a working catalog, which is represented by the red crosses here. And then the Gaia detections of sources in the initial data treatment and their initial best guess of the astrometry tries to associate sources, detections, sorry, to sources in the Gaia catalog, the working catalog. And so you can see for the things as they sort of start to fall in the gaps, it's a bit ambiguous as to which source you should match a detection to. So all of these in the formal data releases, they go through a much more iterative exploration of the scene of every Gaia source and do a much better probabilistic matching. But for the data we work with on a daily basis, which doesn't have this iterative processing, then it's just a nearest neighbor simple matching algorithm, which leads to some issues and some problems. There's also a magnitude term in that matching, so they expect the sources to be similar magnitudes. And if they're very deviant, that means the source may not be matched, even though it's positionally coincident. That can lead to some interesting features in our light curves. So what we're dealing with every day is a very, very large number, up to 10 to the 8 transits. And the team on the right, essentially are responsible for building the pipeline that had to handle these. And what we have to do is basically weed out a lot of the garbage and say, is this a good transit? Do we trust the photometry? Do we trust the astrometry? And then if so, we run our detection algorithms, which are the ones I showed a few slides ago. And that gives us of order 1,000, a few thousand candidate alerts per day. And then we have to explore the scene of each of these. And this is something Diana Harrison developed, where we do essentially the best job we can at interpreting whether this is a real or whether this is a bogus event based on proximity to neighbors. And the neighbors can even be quite faint and still cause problems for us. That leaves us about 20 or 30 events that need to be eyeballed by human beings. And eyeballing involves exploring the light curves, looking at the uncalibrated spectra, looking at the environment of the source, and trying to decide if we believe this to be real or to be a false alert, which results in publication currently of order 10 events per day. And the eyeballing team, the people on the left, are the people who've been doing the bulk of the work of the eyeball for our alert stream. And so just to put these numbers in context, this is a function of time over 4 years, is what is the number of transits we see in our database. So we ingest all of these. Our database is now stuffed full of Gaia data. And we have to weed it down to the thing in blue, which is the number of things the alert pipe detects. And then after filtering, the number of things that we have to eyeball is shown in red. And then the number that we publish is shown in black. So we have these many, many orders of magnitude step change in the amount of data as it goes through this sort of complex sieve that took quite a long time to develop and get to work reliably and robustly. Most of the things that we throw away are thrown away in alert pipe itself, and they're obviously problematic because they're in the wings of a bright star or close to a planet, or they have a very nearby reasonably bright neighbor. Or there's known to be a solar system object coincident with the source that we're looking at the time that we're looking. Or it's known to be a variable star in Gaia data release 2. That was our most up-to-date catalog. Or we see that it correlates with having a very high amplitude historically and having a very red color. And so that's another way we reject obvious known sources of contamination to the transient stream. But the other thing we found quite early on is there are persistent sources of contamination which are more subtle. And so not just being in the wings of a bright star, but actually having a near neighbor which can be slightly fainter even. And depending on the angle that Gaia is scanning at, then the rectangular window where the flux measurement is made can sometimes line up such that that source is in the same window and increases the brightness of our source. Whereas at all other scanning angles, they don't line up. And so we see these sources very quiet and suddenly blip up a little bit. So this is the, I wonder if I can go backwards. Apparently I can't change my slide. Okay, I shall carry on. Our publication delay, this is the time between observation by Gaia and publication as an alert, is just a little under 3 days. That's the median time. And we're dominated here by a number of issues. One is the data downlinked on a daily basis. So there could be, before downlink, anything up to 24 hours delay before the data even come to terra firma. It can even be longer. Sometimes when we go through crowded regions, then the data for faint sources, and we're mostly interested in fainter sources, are held on board for much longer. They have lower priority in the downlink. The next problem is that the data need to be processed in Spain, in Madrid, and this is the initial data treatment, which is a remarkable, it does an incredible job of matching transits that are observed today or yesterday with the Gaia working catalog, the Gaia source working catalog. And that's no small feat, and it works really reliably nearly all the time. Then those data, once that run has finished, those data are sent to the UK, they're sent all around Europe, but we're one of the recipients of that data. And when we get them, then we have to run our pipeline, which again adds, could be 6 hours for very crowded regions. It can even be up to a day to process the data ourselves. So that means our transient survey is never going to be as fast as many of the other transient surveys. But that's okay, because the Gaia scanning law means that the median time between observations, pairs of observations, is more like a month. So in that sense, we are, as long as we're shorter than that, then that means there's still value. And so I've updated the number, but not updated the picture. But this is the cumulative number of transits we published as a function of time through the survey. And this is the picture from the paper. And so we see this sort of increasing rate of transient discovery. And the increase, we're now at 18,000 alerts that we've published since September 2014. And that increase comes with improvement in our system. So as we've gone through, we've learned how to do things better, because we didn't know what the Gaia sky looked like to begin with. And again, because we don't have the luxury of anything other than a real-time processing chain, we have to deal with the data as we have them at the time that we have them. That means everything we build has to be efficient and fast to run. Otherwise, it becomes a wasted effort. And so that meant the whole processing improved over time as we learned how to throw away, mostly how to throw away spurious events, which meant that we could trust better the things that we're publishing. So that's why this is a gently increasing function, which has now been stable since 2019, and we continue at this rate. We anticipate a few changes, and I'll talk about those later, but the alert stream that we published, that most of you have seen, will carry on a very similar rate. The value of the Gaia alert stream has a number of important things that are worth mentioning. One is the photometry. We use a photometric one-day calibration, which uses historic data to predict the calibration going forwards. So as long as Gaia stays stable, then this calibration will work very well. As soon as Gaia goes out of kilter, if there was a need for another decontamination, for example, then the photometric one-day calibration would take time to propagate for us to get the same precision. But so far, Gaia has been beautifully stable. And that means using this very simplistic calibration model, we're doing 1% photometry down to about 15th magnitude, and 19th magnitude is about 3% the calibration. And we update this on roughly a monthly timescale. And the astrometry is where Gaia really shines. Even with the initial data treatment, which uses a simplistic model of the Gaia attitude to solve for the right ascension declination of any detection on the sky, our analysis shows that the astrometry is good to 55 milliarc seconds. So of course, in the future, for alerts that get published, eventually through the formal Gaia data releases, and ultimately with their epoch astrometry, this will be orders of magnitude better. But still, at the time of publication of these transients, this is still seen to be the gold standard, the ground truth of any transient that's published that we also see. So much so that the transient naming server update the astrometry of any supernova or anything that they've published in their archive with the astrometry from our system when that becomes public to them. The real strength of Gaia compared to many of the other surveys, not all of them, is that it's all sky. So we are not afraid of the galactic plane. For reasons I'll come on to, we are a bit afraid of it, but nevertheless, we still carry on and we publish all sky transients. And I don't know if it was obvious in the previous slide. The gray line here is the number of the transients that we published that are classified. So it's 25% of them are classified, which is a healthy number. And this is the breakdown by class. And 60% of them nearly are supernovae. And then the rest go into AGN, CVs, young stellar objects, and so on. This breakdown is not representative of the true underlying nature of the alerts we publish. It is biased by the fact that the supernovae community are extremely motivated to follow them up and classify them. And there are many transient surveys with many classification surveys specifically chasing after supernovae. The other science areas are not so sort of invested in the follow-up and classification. So this 60% bias in this view, on the left-hand side, this is the spatial distribution galactic coordinates of classified alerts on the left and unclassified alerts on the right. And you see those two panels are anti-correlated. The unclassified alerts are by far dominated by galactic plane sources, whereas classified alerts avoid galactic plane sources. So the conclusion from this is that most of the unclassified alerts are galactic in origin. Thus, that 60% or so being supernovae is obviously not representative of what we're publishing. We've done a little bit of work on classification, and we did include that in the paper. And this is a simplistic color absolute magnitude selection based on alerts we published that had counterparts in DR2. So they have parallaxes in DR2. And on the left-hand side, they're labeled blue if they were classified as a CV. This is spectroscopically, or red if they're classified as a YSO. So we built a simple classifier to apply to the rest of the alerts, which had parallaxes, but didn't have classification labels. And so those are shown in the right-hand panel, and then the red-blue dividing with the white line, but between it shows the how the machine performs probabilistically in the classification of objects. So we published that list of objects, and it'd be very nice to see if we're right, if we really have 600, and these are quite high probability classifications. We actually published more with lower probabilities. But we argued that there's significant numbers of new CVs and previously unclassified young stellar objects in our alert stream. And the other thing that's very exciting, and you're going to have a talk about it on Thursday, Adam Kawash, apologies if I pronounced your name wrong, incorrectly, Adam. Adam's been sharing some emails with me recently, and then I was very happy to see this ATEL come out the other day that we're in the year of the highest number of confirmed novae in any year ever on record. And Gaia is contributing to novae discovery, galactic novae discovery. And Adam's going to talk to you about that in a couple of days. We computed two things. How am I doing for time, Lukash?
5 more minutes.
5 minutes.
6.
5 minutes. So two other points about our alert stream. One is we argue, and we go into some detail in the paper about how we compute it, that we're a very uncontaminated survey. It's a very pure survey. We tried to measure the purity of it by looking at regions of high galactic latitude and showed that our purity, and if anybody else published something independently at the same coordinates, or it was classified, then we said that must be a real event. We showed that the purity is at least 70%, and for things brighter than 17th mag, it's more like 93%. And then we explored the environments of the, low galactic latitude sources in more crowded regions and showed that there's basically no spatial difference in distribution of contaminants around the sources we're publishing at low latitude. So we make a claim that basically our stream is very pure. There are very few things in there that are artifacts of the instrument. The other thing, and so these are the figures trying to argue that there's no difference between high latitude and low latitude samples. The other thing we tried to measure, and this is really hard to do, or hard to interpret perhaps, is the completeness of the science alert stream. And so we did this using supernovae because they're long-lived, they're reasonably plentiful in number. And so we used a sample of 2,800 supernovae from 2016 until 2020 that we observed or scanned with Gaia that were brighter than 19th magnitude. And we looked at basically, did we see them or not in Gaia? And what we saw is it strongly depends on the number of times Gaia scanned the position. And so if Gaia scanned it with 0 or 1 scans, then we have very low completeness there. But as soon as we have 2 or more scans with Gaia during the timescale of the event, then we have a reasonable chance of seeing it. And so if you sum up under that completeness histogram, the top curve, then our external completeness for these long-lived transients, it says nothing about short-lived transients, but for long-lived transients is 46%. And of the transients, the supernovae we detected, then 40% of them, we saw them first, which given our low cadence is encouraging. We see no dependence really on magnitude, so it's more or less flat. At bright magnitudes, we're limited to small number statistics. But even going down to 19th, there seems to be no significant roll-off. It doesn't get much worse between 15th magnitude and 19th magnitude. But then there is one issue which does have an impact. So if I look at the completeness as a function of separation from the center of galaxies, and we use 2 mass extended source catalog as a collection of galaxies, then within about 3 arc seconds of the core of a galaxy, then we see a dramatic fall off in the number of supernovae that we recover. So this suggests that basically as soon as environment becomes complex or you're near another source on top of another source, then the chances of missing that event increases. And that says quite a lot about completeness in crowded regions as well as the centers of galaxies. The problem comes from, we feel, that the initial data treatment, when it's doing this initial assignment of a source to a detection to a source, quite often is confused and doesn't necessarily assign it consistently to the same source. And because of the way our detection system works, we need that to have happened. So we're missing definitely some events in crowded regions or in centers of galaxies. Susanna talked about that in the past. She also found a similar effect. So just to wrap up, this is progress since the last time we talked, a year ago, I guess. Testing is ongoing with this single field of view alerts, and we're going to hear a talk from Sumedha Biswas on Tuesday, so that's tomorrow. The idea here is to simultaneously observe them with the Meerlicht telescope in South Africa and see what these are. We've been publishing them on our website so that we can do science with that stream. And it's still open and we're still putting data on there. I think we actually just stopped at the beginning of November. We're also getting ready for getting a fully automated alert stream to take the humans out. So Gabon Martin will talk about that on Tuesday as well. And his case, his argument is that we can replace the humans with a machine that's been trained by the humans. And so this is very encouraging to see. It works incredibly well, and he'll tell us all about that on Tuesday. We published the paper, that's out. We're experimenting with using a periodogram to do better at filtering out the periodic variables, which we still have to eyeball and reject manually. So Susanna's been working on that, and we will probably have that added as a filter. And we will include alerts from the first 3 years of the Gaia mission in Gaia Data Release 3, which we expect first half of next year. I think I should probably wrap up because the others are going to talk about these in a lot more detail on Tuesday. And instead of a summary, because it's such a short talk, I'll leave you with a movie and take any questions. Thank you very much for your time.
Thank you. Excellent. We have some questions here in the chat. Ashish, would you like to ask your question?
Sure. What I was asking was related to slide 10. It seemed that the classification rate seems to go down, which doesn't make sense. And I think it simply means that it's not representing some of the things that you want to.
I'm trying to get back to, right. I've got my slides back. So we have to take all this with a pinch of salt and think about what's going on here. So the classification rate will only ever increase as we go forward in time, which means you see artifacts in the gray line, because what tends to happen is the classification rate for supernovae is quite instantaneous. But then over time, things that get classified late on will be the microlensing events or I don't know, various class things take more time to get classified, so they catch up later on. And so I think this is an underrepresentation of what the true classification rate will be.
Right. Okay.
So,
yes,
so it will never follow exactly the
other one. Okay, thanks.
Okay, another question is from Michelle Denefeld. Michelle, would you like to?
Yes, simply, Simon, the 25% of objects classified, are they all from ground-based, or some of them are classified from Gaia alerts directly? Because sometimes you say a type 1 supernova is quite secure from Gaia alerts.
Right. So no, these are actually all from follow-up. It's nearly all spectroscopic. We allow things to, in my counting, my statistic, I only allow them in if they're spectroscopically classified, or the microlensing team tell me this is a bona fide microlensing event. But that's the only way. They're all spectroscopically classified in this figure. We sometimes, when we publish an event, we will tag it and say candidate supernovae. That's about as far as we go with our predicted classifications and with the comments that we attach to every published alert.
Yeah, and when we have some ground-based classification, how do we transmit that to you or anywhere to be introduced in the Gaia Alerts catalog?
Yeah, so what we do is we scrape, and I didn't put the slide up, but we have a giant database filled with transient name server, but many other references as well. And we automatically check those every day. And if something's been classified in one of those publicly available databases, then we add it to our classification list. Does that answer your question, Michelle?
Yeah, yes, thank you. So anyway, if we have some classification which is not published in a transient database or something like that, then it will not be taken into account, even if we send it to you directly, or?
No, if you send it to me directly, I can add it in manually. But for the rest of the community, the worldwide community, it's better to put it in TNS because then many people will see it, not just me.
Okay, thank you.
I would recommend. Thank you.
Okay, thank you, Simon.
Thank you,
I think
Łukasz.
we have to move on. So thanks for this, and you can stay online, and then maybe people can have also some questions on Slack, to what I strongly encourage people to. Thank you. We move on to the last talk before coffee break, which is Fraser Lewis telling us about what can we do with, how can we teach people astronomy with Gaia alerts.
I can certainly try, Łukasz. Can you hear me okay?
Yes,
you can see the slides okay?
As well.
Fantastic.
Yeah.
So, yeah, another person, I'm afraid, like Simon, who's stuck in the cold in the UK, rather than being in slightly sunnier, warmer Greece. Yeah, I'll tell you a little bit about the education stuff that we've been doing. Some of this will be familiar to you if you've seen talks from me in previous Gaia workshops, but we'll go through some bits and bobs anyway, and then happy to take questions. There are, as you probably know, there are robotic telescopes out there that work in education. Aperture is kind of king. The larger the telescope you have to a broad amount anyway, you can do kind of better science. You'll be seeing talks today and I think tomorrow as well from Rachel Street, who is LCO, and Helen Jernak from Liverpool Telescope. So I don't want to talk too much about the specifics of those networks and telescopes, just to say that I'm in a really lucky position that I work with both Falk's Telescope Project, which has Las Cumbres Observatory, LCO time, and National Schools Observatory, which has Liverpool Telescope time. So I try and make the best of that and try and do some science and some education along the way as well. That's the LCO, the Las Cumbres Observatory network of telescopes, which I'm sure many of you are familiar with, so I won't preach too much on that. And there's a nice little image there of Liverpool Telescope, which, as you might imagine, is in La Palma and not in Liverpool for fairly obvious reasons. We've been working with Simon, with Łukasz, with Jerry and others, producing documentation, producing resources, activities for teachers, and there are some web links there at the bottom. And again, if you miss them in the presentation, just drop me an email. I can pass these on to you. But these are kind of PDFs that we create for teachers to work with students on the astronomy that Gaia does, but also sometimes the other aspects of what we call STEM: science, technology, engineering, and maths. So we talk about the way that Gaia collects its data, the way that it transmits data, the way that it processes the CCD, and so on. So we kind of try and incorporate various aspects of that. And as part of my work as National Schools Observatory, and I appreciate this isn't directly Gaia related, but you'll see why I'm explaining hopefully in a few minutes, we've been creating fairly large web-based activities, which we call teacher free, and we sort of worry a little bit when we say teacher free, but what we're trying to do is create a resource that a teacher can point good students at, and they can just go away and explore these. They're in the style what we call of IBSI, inquiry-based science education, or teacher-free project type activities. So not an activity that a student would work through in 30 minutes or 60 minutes, but something a lot more involved. But we do try and look at the curriculum, and the curriculum is a problem because in Greece, they have a very different curriculum to Portugal, to Spain, to Poland. By the time you move to the UK, there are 4 national curriculums and 6 examining boards, so things get out of hand very, very quickly. But things like the color magnitude, life cycle of stars, the age and expansion of the universe, they exist in curricula across the world. So we've kind of taken that, and we're using real data from our telescopes to allow students to perform photometry and create their own HR diagrams. As part of an extension activity that we created a new activity last year. We were funded by the UK Research Institute, and we created an activity on supernovae, which again, kind of capture kids' imagination of the objects that Gaia Alerts finds. Supernova probably the easiest one to work on, and I appreciate I don't mean the science of supernova is necessarily easier, but it's much easier to sort of impart that information. We show the students how to use a photometry tool, which in this case is an online browser-based tool with Excel, collaborating amongst groups of students, and they can calculate the peak brightness of their supernova and use that to add a data point to the Hubble plot. So in the case of this activity, it's a few hours work to go from measuring Gaia alerts and supernovae to the expansion and age of the universe. So it's quite a all-encompassing activity there. We anticipate using Gaia alerts to do additional plots of these objects for the foreseeable, and obviously we're aware that Vera Rubin Observatory is going to come along and sort of continue that work into the future. When we do that, there are all sorts of things that we need to add in. We need to think about how we select the right targets, how we find which targets are visible in the sky for the students, how we analyze those. And we can't analyze those in a black box way, much as that's the simplest way that we, as scientists do it. Students need to kind of dive into that themselves. And we need to do that with Windows-based software, ideally, and further free software. So we think about things like Salsa J, Macaulay, JS9, AstroImage-J as different packages, and using the ideas of Excel and Google spreadsheets as well along the way. We think that this allows our students to get an indication or a feel for the scientific process. This idea of collecting data, analyzing it, reporting on the data, the collaborative nature of science, all those things are kind of in the activities that we create. We also sneak some maths in, hopefully without them noticing. But we're always talking about periodicity, trend lines. We're working with logarithms and error bars. And we're getting the students involved in kind of independent research and thinking about spin-off projects and ways that they can take their studies further. There are problems in creating these activities. I'm happy to discuss those, just as happy as discussing the good bits. But it is difficult sometimes, particularly with teachers, in terms of installing software. We have students that are working on laptops, on tablets, on phones, well, not so much on Linux, but on Mac machines as well. So there's always issues around software, and we kind of have to conquer this idea that the student works for 30 minutes, writes down the answer is 12, and they're done and they go home. That's not the kind of learning outcomes we want from these activities. So we provide them with sample data sets. We encourage them to go out and then collect further data on objects to do their own studies. Ownership of data, I think, is really useful in terms of getting them inspired. One of the other things is timescales. We work with kids who are 14, 15, 16 years old. As an example of a paper recently that we were fortunate enough to get our teacher and student on, it took 2 years from the time that we collected the data till the time the data were published. So it's not an immediate response in that sense. But yeah, there was a really, really nice paper that we were very pleased to be on, which was this one by Jaroslav Merch, who produced this paper a couple of years ago. And we were fortunate enough to get our teacher and pupil name checked on that one, which we're really pleased about. We put monthly targets on our website. So every month we put a few targets of things that are in the sky, the regular Messier type objects in general, but we've started doing Gaia targets as well, more focused effort. To date, not many images. So in collecting those numbers today, I realized just how poor we've been in actually inspiring people to take Gaia images, but we will, now I see that, I think I can try and push that a little bit further. In addition to that, there's a current micro lens that I'm aware of, that I'm taking data of. It's very, very handy when Gaia Alerts finds objects that are 12th magnitude, or become 12th magnitude, let's say, because it allows us to go onto the smaller telescopes in the network, which makes things a lot easier from our images, from our point of view. And again, not related directly to Gaia Alerts, but the idea of exploring DR2, DR3 with things like TopCat, producing color magnitude diagrams, is something that we're really, in various forms, I'm really starting to think that we need to do more of. I'm going to try and finish off. I appreciate I stand between you and the coffee break, so I won't overrun my time, I promise. But I wanted to mention this project that we've just become involved in, called Last Skill. I'm the UK, for whatever reason, they've made me the lead of this project. It's an Erasmus Plus project running for 2 years, and we're working with colleagues, friends in EA and Nucleo, who are people we've worked with for many, many years in Greece and Portugal, who are scientists and educators in equal measure. We're also working with Vasilis in Skinakis, who will be one of our partners, coming and producing resources alongside us, and also the Austrian Space Forum. So a real mixed bag, if you like, of partners here, but a really nice project that we're involved in. We're actually that's essentially our remit, looking at the kind of during and post-pandemic, the idea of online learning, data archives, big data, all these things that they're all buzzwords that we as outreach and educators know about, but we were successful in getting some funding for this one, and to try and work with teachers in those countries in particular. You know about big data. I don't need to turn up at a Gaia conference and tell you that big data is a good thing or an important thing or a current thing, but big data is the way forward. We've got James Webb and CERN, which is more physics than astronomy, SKA, LOFAR, LSST, and so on top of Gaia. So there is big data out there. How accessible it is to people and what they can do with the data is the key. That's the hard bit from our point of view. So our remit on LaSkill is to produce digital resources, looking at advanced ICT tools. I appreciate this is slightly vague, but it kind of gives you an idea of the buzzwords that we've put into the bid to be successful. Where we can make them interdisciplinary, so much the better. So if we can think about how we incorporate maths, how we incorporate biology, chemistry, and so on, alongside astronomy, then that's a really, really good thing from our point of view. We are creating resources currently, and we're looking to recruit schools. So if you are based anywhere in Europe and you have schools or teachers that you work with that you think would be interested in this, please contact me. But we're going to run some real week-long summer schools next year, one in Crete, where you're based right now, and one in Portugal in 2023, where we'll be working with teachers for a full week to try and look at resources and online tools and so on. Those resources will be made available in those foreign, that's awful, following languages, English, German, Portuguese, and Greek in this case. They will then be shared with the European Union countries in terms of our website, but of course, it's then freely available to people from all around the world to get involved in. That's it, I think. Thank you very much for listening. I hope I haven't taken you too far away from the science that Gaia Alerts is doing just by mentioning education at this point, but happy to take any questions, happy to take any emails that you send me to work with you in the future. Thank you.
Okay, thank you very much. Thank you, Fraser. I just have a comment that I'm very pleased that you're observing Gaia 21 EFS, and if you need any help with data processing, we have tools for this. We can help, and actually this is something what I would like to discuss with you as well, how to combine our resources we're building, the infrastructure as well, maybe in this new framework you mentioned. So I will definitely send you an email.
Yeah,
Thanks.
by all means, please do.
Any other comments from the audience or from Zoom or YouTube?
It's coffee time, Łukasz. They're all going to go and have coffee.
It is coffee time in 2 minutes. So anyway, okay. So thank you, Fraser, very much.
No worries.
Thanks for joining us. And we'll stop here and go for a coffee break for half an hour. I will leave the Zoom open, and I will leave the YouTube open as well, so that nothing breaks. Piotr, if you could share. Right. We are back after the break. If the mic is on. Yes, I'm on. And yes, and I'm afraid our next speaker did not show up yet. But we are so fortunate that we have a perfect replacement of Jean-Gabriel. Agnieszka Słowikowska is actually the chairperson of the ORP, and she kindly agreed to take over. So I give the floor to Anna to tell us about the ORP, our sponsor.
Yeah, great.
And you have to mute everything, Aga.
Yes, sure, sorry. Okay.
You want to go out?
No,
it's fine.
Okay. Welcome, everyone. I wasn't expecting to give a talk today, but I hope, and the presentation honestly. Oh, no, it's not working this way. Yeah. And the presentation is from European Week of Astronomy, where there was a meeting organized also by UKASH. So sorry, the slides are a bit off, but I hope they contain all the information that I needed. So as you all know, this ORP stands for Optical Radio Not Pylon, and this is the result of more than 20 years of collaboration within the optical that probably most of you know very well, and also there was simultaneously there was a radio program that was devoted to the radio astronomy network, and both of these networks they recently just joined, and from that we have this optical radio network. So. Okay, so the grant is funded from the European Union. It's for 4 years. It started on 1st of March this year, and the budget is 15 million euro, and the program is coordinated by CNRS. And today Jean-Gabriel was supposed to give him this talk as a representative for the Coordinate Institute. And then there are also Max Planck is coordinating the radio part, and then of course the optical part is coordinated by the University of Cambridge. There are 37 institutes from 16 countries. The logos of these institutes I have on slide, and probably most of them you know already very well. So the ORP aims are listed here. It's to form a comprehensive set of research infrastructure in related domains of optical and radio astronomy, to support a harmonized access procedure, to unify data interfaces, to improve service towards scientific excellence, and to train an entirely new generation of astronomers. Here are the objectives that you can also find out on the webpage of ORP. So maybe I will not read all of them, just read the main titles. So of course we provide the transnational access and visual access. We are going to improve the service, harmonize process, to develop the common standards for observation request and specification, to develop online services, mapping and analyzing access modalities, to foster exchange of good practice among stakeholders, and contribute to astronomy to effort to raise the awareness of and mitigate against the effects of low Earth satellite constellation. And as we maybe some of you were joining, but there was recently the meeting regarding the low Earth satellites, and review and understand the basis of access provision for all current and future facilities. So one of the biggest points are, of course, this transnational and virtual access telescopes and facilities. And you can see there is radio and optical infrastructure maps. And you can go to the ORP webpage, where we can then later on during the discussion we can open, and you can always find there the news about the open calls for optical and radio infrastructures. Here is this all the radio telescopes that are in the radio part, in the radio net, and then also we have the list of the optical telescopes that are in ORP. If you you can just open in your browser the ORP webpage, and then you can find all the necessary information. There is also one of the work packages is also virtual access, and this is for the LOFAR and Alta. And again, you can go to the webpage and open this virtual access in the support pages. We are also going to provide services, and this is the most important are, of course, training, common principles and tools, and facility support. And within the training, we are going to organize training schools. And so some of them, they have been already organized, as well as the specialized schools and workshops. And within the common principles and tools, we have harmonized access tool for proposal. And this is, I think it's a pretty challenging task to do, to get together all those proposal tools, and then services to facilitate multi-instrument and multi-wavelength service projects, harmonized and seamless approach to access and process of the data. It's also probably not very straightforward thing to do. Platform of exchange for collective experience, and also platform of exchange of sharing experience and resources across the pilot partners. And we are also going to develop and implement improvements in facilities and their instrumentation, and improve the infrastructure services. So the last was, this you can probably still find on the, I think it was the recording, you can find still on the web from the talks that were given about ORP during the European Week of Astronomy. But as I mentioned, we can go to the web page. Can you have to change the you can go to the ORP webpage, nothing there. And then, of course, you can find the general information, the mission, the objectives, the partners, as I already shown. Then there is the link to transnational access and visual access, and you can check the infrastructure. But probably what is most interesting is, of course, the call for proposal from different optical or radio telescopes or the radio telescope networks. So you can find all the recent open calls here on this in this link. And then we also have the then we can also apply for the visual access. And you can find the two links that I've shown in the presentation as well. And also you have the link for services, for training, and so on. Probably it's all useful to go and visit this webpage with the news from time to time. And as you can see, this workshop is also advertised there. And there was also, as I mentioned, this workshop on observing the skies. It was recently in October. And there is also a JA4 training group meeting that was in October. in October. This is news. Then you can also check the forthcoming events in the calendar, so you can check what is coming. Then of course resources, the contact, and then you have also the contact, and then of course there is internal also web page that people that are involved in ORP can use. If Vasilis is with us, as he is Vasilis Kondaris for the University of Crete, he's vice chair, so maybe Vasilis wants to comment or add something.
He's not there.
He's not with us. Okay, so this will be all, and then we can try to answer the questions.
Okay, thank you very much. Thanks. I just add that Aga was asked to give this talk like 10 minutes before, so thanks, appreciate it. Any comments, questions? We have some time left for discussion here in the audience or Zoom. I can definitely comment on what Aga mentioned, is that this transnational access is probably where most of the money goes in our grant, because it's very costly to buy telescope time. And we buy time on the best machines, biggest guns available, both in optical and radio. Not every telescope time is for sale, right? For example, Keck, if we were able to, we would probably buy some. But this is not accessible so easily. But there are other large telescopes which are available through us, and for you they are free of charge, right? You just have to apply to us instead of those telescopes, and then you get accepted or not. But then you can get access to biggest telescopes in the world through us. And this is John Davis mostly from the optical side. He's leading this, has been leading it for the last 20 years very successfully. The time allocation committee is composed of high-profile researchers. They review. They're actually Opticon. They have been and they will be the proposal writing schools dedicated to this, how to write an efficient proposal to get accepted in Opticon. So it's not easy to get the time, we must admit. It's highly competitive, but this is an additional channel you can access the telescope, otherwise not available to many. So just a comment. I don't know how it goes on the radio side, maybe.
I can comment on that, but I think what is also important, and now it's going on, is that we are starting to discuss how to prepare this platform for joint proposal. I mean, it's absolutely not trivial. And there is also one important issue in that how to do is that the proposers are anonymous. It's something which is, I don't know if you, I mean, for example, Hubble, now they have this form, and you can already analyze the results that when the PI is not known, apparently, also more women they get time, and also from more favored institutes.
Right.
So there is really strong bias on that, and there is a really a big discussion how to really do it. And as I mentioned, it's not really trivial.
How do you do it? I mean, Hubble?
First of all, you have to write the proposal in a way that it shouldn't be obvious who is the author. Okay. Then the reviewers, they don't really see your name, your institute. Basically, they see just the scientific justification and then the number, and that's all. So, the proposal might be rejected if it's clear, if it's written, or while reading, if it's obvious who might be the PI.
This is quite dangerous because this could be subjective, right? This could be unintentional, right?
Yeah.
And anyway, yeah, I know that ESO does it as well. Recently, in ESO, there's also a requirement for this. So it's getting everywhere. Yeah.
But then, of course, it's also the discussion how much information about yourself you as a PI wants to share with others. So how we can really monitor the statistics. I don't know how advanced you are in your career, if you're a female, male, or other sex, or from which institute you are, and so on and so on.
That's GDPR problematic if you want to ask for those things. But it's a bit dualistic, because at one end the EC wants you to investigate how you're doing in this respect with balancing, but at the other hand, it is you're not allowed to ask people these things.
Yes.
So that is sort of a tension field.
But at the end, once the time is allocated, and you know the names of the PRs,
Yes.
so you can always go and Google for their affiliations, right? And then you can do the statistic from which countries people are getting the time, from which institutes, and so on. But the other issue is, of course, imagine that the platform that is joining all the instruments, all the possibilities.
Mm-hmm.
I don't know.
I comment, do you also require that? Oh, sorry. Do you also require that the persons or the PI or the group is able to reduce the data? Because I know that some telescopes do actually require this. They have to explain to them that you're able to do this, because otherwise, I mean, to obtain the data and you do not want to reduce them.
Yeah, this is, yeah, it's a good question, because of
You mean the transnational access telescope?
Well, yeah. So, for example, if a person applies to the
but in principle, in 4 years' time, we should be able to support astronomers to analyze the data or to provide the tools that you,
Yes.
even not being an expert on a given instrument, you should be able to analyze or ask the support to do it for you.
Well, yeah, I can add a sentence about that. That as far as we use we applied within the transnational access in Opticon, the data were calibrated already, and it was done automatically by robots or by the support astronomers. Right? But you use just science-ready data.
Okay.
And I would like to add one thing that Aga has mentioned about the transnational access, but there is also maybe not formalized groups of telescopes within Opticon, within ORP. There is a network of ground-based optical telescopes, and Łukasz will tell about that for a while, right? You will present for a while.
Yeah, after Haro.
Okay.
Yeah, I'm talking.
Okay, so it is also possible to join this group, and you don't have to be in ORP within the transnational access, but also if you have smaller telescopes, you can also join the group and join the network. Right? At this moment, we have more than 100 telescopes spread over the whole globe, and yeah, we are gathering a lot of data from this network. So that's all what I wanted to add.
Yeah, so we are actually, so the network Pavel mentioned is under the umbrella of the virtual access. So formally within the ORP, the researchers, they can go to the virtual access and they say, I don't care which telescope it is. It's a virtual observatory for me. I use the phrase which is known for some time, but I didn't mean the virtual observatory. I didn't mean VR, but this is kind of a observatory. As a scientist, I don't care. I care about my science. I want this target to be observed. And I schedule this, but I'm already getting ahead of myself because I'm going to talk about it in half an hour. So just to pre-advertise.
Just answering the question about the radio. So you can either apply to a single dishes, as you can see on here on the web page, or you can apply for the array within the EDN time. The call was just closed recently in the So.
But this is like if I want to use Jodel Bank, for example, right? Then I go to Jodel Bank and I say, but
Yes.
it's being paid for me, right? I don't have to pay.
Yes.
Right? Okay.
There must be a
Because
call.
Yeah, there must be a call.
yeah, there must be a call.
The
Yes.
list of the call you can find on the web. So, but you can also, I mean, of course, depending what is your science that you want to do, you can go for the EVM as well.
So the European Field BI network is through open skies. Anyone can propose. I mean, there's 3 calls for proposals per year.
Yeah.
And anyone can propose, and it's free of charge.
Yeah.
So this is not within the ORP then. There's no money involved from ORP, right?
Well, we are getting money as each antenna is getting money within the ORP.
Yes.
Of course, it's different fraction of euros, but depending on the yearly or cost per hour of using the antenna. But you are also committing that you will give this, I don't know, 300 hours per year or 500 hours per year for the EVN options observations.
And I suspect that within the ORP project, there will be a separate call for proposals specifically dedicated to multi-wavelength proposals, where you have to propose for multiple things. But I think that is something that still needs to be worked out, right?
Yeah.
So far, we kind of operate like in the old days,
Yes.
optical separately, radio separately, but we are trying to come up with solutions.
That's
That's why it's called pilot.
Yeah, exactly.
I think it will take really some time to join all of them. I mean, it's not really easy. I cannot really, for the moment, imagine the platform that's all that, but you know, you can really pick up whatever instrument or whatever telescope, especially the optical people not necessarily know what are the strong constraints on the radio and then vice versa.
Yes.
Wait for half an hour. Maybe it's better.
But I have a question to Aga. You showed a map, and that was a map of optical and radio, because there was one dot which intrigued me in Himalayas. There was a dot in Himalayas. What is that? Yeti Observatory.
I don't think it's.
Maybe that would be connected to HCT, the place where they have Himalayan.
Maybe, but that's why I'm asking Aga.
Let me open this small here.
This is the map I know from John. There was another map. Maybe it was on the.
This is the map from June 2021, and I think really nothing should change. And the previous
But these are optical telescopes. This is what John shows for optical.
Yeah. So this is, and I think it's interactive map.
No, I think it was on the website you showed.
Yeah,
Anyway.
the interactive map is on the website. So I was showing this radio, right? EVN, but also the EVN telescopes, but also the single dishes telescopes. Like single instruments. And then you have this map for the optical telescopes.
Okay, I'll look it up. Right.
Okay, I don't know.
Okay, thank you, Aga, then. Let's hear more about the radio part from Haro. Haro, would you like to come forward here, or you?
I would like to go there. But I first need to share my screen.
Share your screen, yes. Because
then I'll come.
Right, people were complaining that it is actually quite faint. So the distance from the microphone, it does matter.
That's what exactly.
Yeah, so please come forward, yes. Maybe we will see you. Oh, yes.
Yes, that's me there. Yeah. Hi. Good afternoon, everyone, both local and remote. I would like to start by saying that there are centimeter wavelength, very long baseline interferometric monitoring programs already running. And one of them is producing movies such as this one. And it is the Mojave project, and they have been actively monitoring active galactic nuclei since, well, actively since about 2002. And they produce many movies. They have a page full of them. But actually the Science Archive has a lot more than that. And this might look somewhat familiar to you by now, because each source that they're monitoring has its own webpage with, for example, the movies here on top. There's historic images in different file formats, fluxes that have been monitored, and if available, light curves, possibly combining different instruments as well. So if you look at the statistics from the project, you see that this is quite a big effort in terms of number of people that are involved, but also how much data they're taking and how much data is being reduced. So the thing that you can ask yourself is, okay, what is behind these movies? Well, at the highest level, obviously, a movie is not rocket science, right? Because it's just this. So the real question we would ask, what is behind these images? And if you take, for example, the images for this particular source, the first and the last image in their collection, you see that it spans a lifetime of 25 years that's been looked at. And most for our purposes, if you look at the X and Y axis scale there, that is a resolution of the image. It is below milli-arc-second resolution that these people are getting. It's crazy. Now, my name is Harov Kouter. I work at the Joint Institute for VLBI in the Netherlands. And I'm here to talk to you about why radio is different and what it is that the EVN might bring into the ORP pilot. So this formula is important because what it actually means in practice is that the largest radio telescope that we have has the highest resolution, and that one gets about 3 pixels across the full moon. And to put that into perspective, that if you put the Andromeda galaxy sort of on the same scale in this picture, this one has maybe a handful of pixels, 10, 15 pixels across the whole galaxy of resolution. And in fact, there's only 2 of these steerable radio telescopes in the world, 100-meter diameter, and all the others are smaller, so the problem for them is even worse. They have even less pixels. So what can you do about this? And one solution is to use a network of sort of smallish radio telescopes and try to see what you can do with that. The European VLBI network is such a network. And it uses a rather loose definition of the word Europe because we have affiliate members in South Africa, China, Korea. And basically what it does, it uses the long baselines between the telescopes to simulate a telescope with a diameter of 8,000 kilometers. Now, if you put then these numbers into the formula, like the typical radio wavelength and the diameter of your telescope, then you do some conversion to different units, you end up with something like 5 milliarc seconds. And that's how you get these enormous high-resolution images. The thing to realize is that a baseline between 2 telescopes, an interferometer, is nothing more than a one-dimensional imager. It has very high resolution in one direction. But in the perpendicular direction, there's absolutely no resolution whatsoever. You cannot discriminate anything. So how do you make images out of that then? Well, there's a couple of things that you can do. Because if you add more telescopes, then you have more baselines, and then you can have sample different orientations across your source. And then as a second thing, we use the rotation of the Earth to have the baselines rotate across the source. And from all these basically one-dimensional images, if you put them, just stack them on top of each other, you end up with a two-dimensional image. So that's what we do in VLBI. And from some point of view, you could already imagine that VLBI is already a multi-facility observatory, because this only works if you actually coordinate very well all the observations between all the telescopes. Because if one of them is doing something different, it's not going to work for that station. Now, but the real killer is actually calibration of radio data. And there's some reasons for that I will go into, but actually the one that is the most important for radio data is phases, phase calibration. And I will illustrate that very simply. If you take our favorite image analysis image, Lina, and if you just apply a two-dimensional Fourier transform to that image, you get a set of complex numbers, and complex numbers have amplitudes and phases. So if you separate those out, you end up with images that look like this. Now, if you then, from these numbers, try to apply the inverse Fourier transform and see if I cannot get the original image back, then you can immediately see that the level of success that you can achieve with that depends critically on specifically which of those numbers you actually use. In VLBI, we sample this Fourier space. We sample that and we sample it sparsely. We don't have this full plane available. And what you can imagine is that your ability to retrieve the original image on the left-hand side depends on how well the right-hand, the Fourier domain, is sampled. And if we look at two extreme cases, at the top level we have, I used 3 telescopes for 5 minutes looking at one source. And in the bottom, we take the full EVN array, 550 telescopes, and have it observed for 8 hours continuously, and see what kind of impact that has on the imaging. In the top image, you can believe me, it's almost not visible, but the dots or the sampling of the plane, it is there, but it's really, really very small because it's only 5 minutes. So on the right-hand side, you see the resulting imaging capability and these images. This is what in optical you would call the point spread function, or the equivalent thereof. And I've put them here in full size so that you can compare that at the left-hand side, you really don't see anything, and on the right-hand side, you can actually really do some useful imaging. But for calibration, there's another thing that actually bothers us very much. It is the ionosphere. The Earth's ionosphere introduces frequency-dependent phase errors through the radio signal. And worse, the ionosphere is not stable, as you can see in this animation. It is both time variable, but also depends on geographic position. And if you, for example, monitor a calibrator, the persons in this observation have monitored one strong calibrator across 24 or 24 hours, and you see that the phase is reasonably well behaved. But you don't want to look at calibrators only, right? You actually want to look at your science targets. So what we do in VLBI is we cycle between calibrators and target images. And in this particular image, I will leave it up to your own imagination to guess which one is the calibrator and which is the target source. And another thing that this plot illustrates is the geographical dependence of the phase behavior. These are 3 baselines, and you see that the phase behavior is different from which continents you actually combine in your signal. You can ask yourself the question, well, if I do not observe all the time, what does that do to my imaging capabilities of the array? Like this cycling between target and calibration. Well, in these 2 plots, the difference is that in the bottom plot, we still cover the full 8 hours, but only a quarter of the time is spent on the source. So you have 15 minutes looking at the source and 3/4 of an hour doing something else, etc., but have the same 8-hour time span. And what you can see in imaging performance is that it's from a resolution, it's only a bit noisier, but that's the only effect. You can still have very useful imaging capabilities. But imaging is not necessarily the only thing that you can do with radio telescopes. Over here, there's some pictures from gamma ray burst afterglows that emit in the radio, and you have pulsars. They also emit lots of radio emission. And I have indicated in the plots here a flux level of 1 milligensky, where possible. Some of the plots have a slightly different scale, but 1 milligensky. Remember that. You see that it's in these plots. So flux monitoring, you can do that with a single dish, because you're only interested in how much radiation do I receive. But again, this system suffers from exactly the same problem as this. Because the pixels of a single telescope are so big, you're not necessarily, it's not obvious which source you are collecting the radiation from. So what you can do is take 3 small dishes, radio telescopes in the European VLBI network, and if you combine them, then you already immediately forgo that problem. The field of view is so small that you basically already know, okay, this is the flux from that source. And what you can see is that with these 3 telescopes only, in 5 minutes, you can get to a flux level or noise level of already well below a milligensky. And if you observe for an hour with these 3 telescopes, you can go down to 2/10 of a milligensky already. So basically, that is what the EVN, I think, has to bring to the community, imaging and light curves, even at reasonably high time resolution. So what is Jive planning to do within the ORP pilot? The idea is that we develop a plugin for the TOM toolkit that will allow people to, and have it integrated in the black hole TOM that Łukasz will be talking about later, I think. So what we'll do is have a web service deployed at Jive that will actually respond to the requests from the black hole TOM. And that will actually produce an observing schedule based on the source and the mode that the user wants to use the EVN in. And in fact, that's selecting the target and what mode to get from the EVN is only the start of a rather long workflow that will have to be done. And if we look at those steps, is that some of these tasks have already been automated, mostly. Some of these tasks, they might be automated, but they are not covered by the ORP pilot technical development process. And some of the steps in this workflow are probably never going to be able to be automated. So that's a fact that we have to live with. So as for the data reduction part, Jive in other EC projects is developing a Jupyter Hub instance that you can log into, and it has, for example, a dedicated plugin that allows you to search in the EVN archive very quickly your own data by experiment code, for example. But it also has a full-fledged cone search that you can actually search around a particular position and find data. Now, once you've found data in the EVN archive, it's a matter of just double-clicking on this, on the data set, and it will put you into a Jupyter notebook with the best known calibration strategy at that time. Because we keep a version-controlled master Jupyter notebook that we can update if and when better calibration strategies or tools become available. So once you have your data in such a Jupyter notebook, you can start doing the analysis and inspection of the data from there. And if we look at the, calibration pipelines that we are either building or thinking about, there's the last one, the light curve. That should be simpler to do, but it's not on our agenda yet because we have no calls from the community yet. Until now, the EVN mostly is used for imaging. So, but your requests might actually be a driver to that. There's no formal support or planning in the ORP pilot project for this, but if there's user demand, then that actually might be a driver. So, summarizing, I think that the EVN, the European Field Guide Network, definitely has some very interesting science capabilities to add to the community. It's not going to be easy, but we strongly believe that the integration with, for example, a black hole TOM system, that it will significantly lower the barrier for the scientists like you to entry into multi-wavelength observing campaigns. And I think that that is all that I have to say at this point. Thank you.
Perfect. We have some time for more discussions.
Shall I return there? Or
you can return there, but well, remember the microphone is here, so we will be better there. One thing what struck me is that in the optical, well, we do images, but we are mostly interested in light curves. While you are interested in images, and light curves is something, is a kind of last product you can think of. Right?
Yes.
So we come kind of on different directions. So we have to meet somewhere.
Yeah, but I think there's definitely scope for that, and I think that you see what you can do with only 3 telescopes in the network. Yeah. So that might actually also, because if you need less telescopes, it might be easier to get the time, and the data reduction and the data volume will also be smaller. Mm-hmm.
This was basically my question, because we have 3 sessions of EVN each year, right? So you know well in advance when and what you are going to observe. It's very hard to get TMO. So it's not like, that in optical you have another, and in 1 hour you have the radio.
It's not that easy as it does.
So my plan is, of course, then, having the smaller networks of radio telescopes probably it will surely improve this a lot. Right? To be able to schedule whatever simultaneous observation.
I think that is this would demonstrate a very good use case for that kind of application.
But then the radio telescopes, they have to declare that they want to be in this, apart from the EVN sessions, which are like 3 times 4 weeks per year.
Yeah, that's true.
And then, of course, the next question would be, you have to more or less know which flux you expect and which frequency from the sources, right? You have to have some idea. So how you need to kind of estimate that. Right?
Well,
decide at which frequency we want.
Yeah, sure. It applies to the optical as well. We should know the rough level of magnitude, because otherwise we don't expose enough or overexpose, right?
Yeah.
So it applies the same principle.
And we have, so these numbers, we have an online calculator that you can use to play around yourself and say, okay, I need 1.5 hours to reach sort of the noise level to have a 3 or 4 sigma detection. But yeah, that's going to be always the case. And I presume that indeed in optical, you cannot just say, okay, point there and make it, because the first thing people are going to ask, is it 10 minutes or do you need an hour of exposure?
Exactly. So it's kind of the same.
So within the smaller radio networks, how is it going to be organized? I mean, right between the EVN sessions, well, I mean, we're saying, okay, look, we have the request or the radio observations, and whoever is free or willing to join, then.
So my interpretation of the ORP pilot project is to exactly find out how we're going to do this. But that, again, this is my personal interpretation. And I hope that it is somewhat correct, because this is new territory for us as well. Because the EVN is very dedicated. Okay, we have 3 times 4 weeks per year. And as you can see, it is mostly geared towards imaging, because they have longer exposures.
But of course, then you gain the high special resolution.
Yeah, exactly. But if you're signed, but again,
if you want to compare astrometry, then it's fine, right? The Gaia astrometry, the radio astrometry.
Yeah, but it sort of also depends on exactly which science is it that you want to address. And I think, for example, the light curves, they seem to be low-hanging fruit for small telescopes, and not, you don't need 4 weeks of time to do that. And
it's also the question on the how long for the and what will be your time resolution expected, right? Radio time resolution.
Yeah. So now the only drawback that you have to realize is that for a radio telescope, or to set up a VLBI observation, typically takes, well, let's say a day. You cannot just say, okay, I want.
This is what I meant, right?
Yeah.
The answer or of the radio telescope is
because sometimes,
response.
Yeah, but it's, depending on the exact details of which telescope you are requesting, changing frequency, changing observing frequency might be very fast. But some of them, people literally have to go up with a ladder or with a device and to physically change the receiver. Yeah, exactly. So, but for those telescopes where this is easier, you can think of that it can go faster. And I think what might be helpful here is that most of the times radio is a bit late to the party. If something goes transient, usually it goes in the higher energies first, and then radio comes sometime later. Oh, wait. So you have a bit, I think, and the exception are the fast radio bursts.
Forget about that. Yeah, of course, there will be some limitations to that system. Not every science case can be addressed, right? With Gaia alerts, what we started, at the very beginning, we realized that GRBs, they're essentially out of scope. So
because there's no way to respond.
Yeah, as Simon showed, we have 2.5 days or so reaction of seeing the data, right? So it's well gone by the time. So we might have some in the data, but we kind of, this is not the instrument for this. For all the kind of short time scale events, so we are kind of already on a kind of relaxed scale. Of course, we're not limiting ourselves to Gaia alerts only. There are other surveys, and they give you alerts immediately, like milliseconds, like gravitational waves, for example, right? Again, so we can respond to this, but we don't kind of have to if there is this lag, kind of natural lag, And as you say, TO is not easy with radio, and nor in optical.
Like monitoring.
But you're facing transients. You're saying transients, but we should not limit ourselves to transients only. I would like to emphasize this, that even with all the time domain, that's why we call it time domain, not transient anymore. Boring eclipsing binaries, they do it all the time. Sorry, Laura, I know that you like them. There could be an excellent science cases for those eclipsing binaries. If you find one, I don't know, one which is in radio, and then you have 10 years of observations of one target, and then you do something amazing with this, right? So this is time domain, multi-wavelength time domain. So for that, you don't need to react quickly. You observe whenever you can. That's what we do in our system, actually. We in the optical, we are even more affected by the weather. So even there is a supernova in M81, we have to wait for the weather, which gives us another delay, right? So, yeah, so relax.
I think that within the subsets of radio antennas, like, different configuration of 3 or 4, this is doable. For the EVN and so on.
Sure, let's start with something simple.
Yeah, exactly. Let's start with something simple and see if we can make it work. Because already trying that you can do it from one place, because you already mentioned that yourself. The integration is, I think, step 1. And then let's see if we can make it useful.
Yes.
And what kind of practical things do you run into?
Of course, the big dish as FLSWare, I mean, they can do a lot of science also as a single dish. So then the question is, how many hours are they going to devote between to be, the small network and so on? And it's a question for each single person.
Yes, I think, well, if I tend to think of this as a technical issue in the sense, if it's just a matter of when is your telescope available. And then if you have a matrix of time versus availability, then you can easily say, okay, at this time, and the EVN session would fit in there.
But on the other hand, I absolutely agree that when you have the smaller class radio telescope, like 2030, they make really much more when they are in a subset, like 3 or 4, than when they are single dishes. I mean, for single dishes, you can do what we are doing all the time, the monitoring of lasers and so on. But you open wider for the science cases when you really collaborate within smaller even networks. Because of course 22, I mean, 20 meters.
So, but that's specifically why I chose those only 3 of those.
Yeah, because I think they are also easier to. I mean, they are more available, so they have more time that they can really share.
In general, yes.
So for us, the optical people, we understand images, right? And then extract astrometry, photometry from that. And this is where I think we overlap. We also do images. The way you get to the images is way more complex. But this is, this is where we overlap, right? But also, we are dealing with multidimensional data sets and trying to incorporate them in our time domain work here, which are spectroscopic observations, right? This is not time measurement. This is time and a vector of measurements, right? Yeah. And it's not easy to handle. We're working on it, how to include it in our system as well. So in that sense, the radio is yet another kind of multidimensional data set.
And frankly, if you look at a radio observation, how it works, the technical aspect, it is already a spectrum.
Yeah,
that's right. We do the calibration basically by frequency for every frequency.
And it's an image as well.
Before you make an image, you have to do because only at the end for the imaging, that's where you collapse the frequency dimension and you add everything into one.
That's right.
Moreover, you have also polarimetry.
Yeah, well, there's because
almost for free. I mean, it's not that straightforward, but yeah.
Yeah,
I think that is still sort of the black belt part.
Yes, this is for the pilot squared. Yeah, next pilot.
No, but the data. Once you take the data, you have it.
You have it, but then.
And if it's in the archive, you can later on you can decide to do something with polarization.
So my question is actually, what is the science product the scientists are looking for when they are interested in radio targets. How people do science. The people take images, right? But I mean in time domain already, right? In the radio. What is the kind of the ultimate, the most common product scientists are looking for when using radio telescopes?
I think it would still be images.
Images.
Yeah, because you want to get high resolution images of the black hole jets and
then you check morphology and stuff.
Yeah, but also people look at masers and galactic sources because you can see the maser spots around a star.
Yeah.
And then you can actually see the rotation that's being used. Supernova remnants.
Right.
People.
Yes. Well, there is of course an avenue within optical. People do the same in the optical imaging. This is not what we are doing. Right?
No.
So we're more after long-term flux measurements.
Yes.
So if this is where we can meet that.
But in principle, I think that having sometimes a source image at radio might not actually hinder your science. Might actually help improve your science. I don't know.
True. But I'm thinking about services on the systems. So right. Cool. Excellent. So
shall I unshare?
You can unshare, please. Thank you very much, Haro. So the next speaker was supposed to be Rachel Street, joining us from California, but probably because of my mixing up all the possible ways, all the time zones. What? Sorry?
There's also one hand raised for the questions.
Vladimir, do you want to ask a question? Right? Yes. Because you raised your hand in Zoom. No. Okay. I will lower this. Okay. Thanks. Well, let's see. Maybe Rachel joins us later. I wanted to give Rachel the floor for introducing the TOM system. She was one of the. Oh, Jean-Gabriel.
Lucas, I'm sorry. I'm realizing that I probably missed the right time. Did I?
Yes. Hi. We can all see you and hear you. Agnieszka was so kind that she did a talk on your behalf, and so yes. Thanks for joining us.
I apologize, really. I'm sorry. I saw CET on the or ECT on the schedule, and I thought this was a continental European time.
That's what I thought a few days ago, exactly. So it's my fault. Me to blame.
Ah, okay. So are you expecting me to do anything, or you're good?
I will just, we can see you here. Everyone can see you here. I will just introduce you, and we have to move on with the agenda. Yeah. So Jean-Gabriel, as Agnieszka mentioned, he's leading this huge consortium as the main coordinator from the CNRS French part. But I think Agnieszka did a very good job introducing the ORP. So thank you, Jean-Gabriel.
Okay, well, thank you. So again, apologies for
no problem
for missing the right time, and I wish you. I'm sorry that I cannot be with you. I am actually at Observatoire de Haute-Provence, and we are also discussing time domain stuff, but in relation to gamma ray bursts with in the context of a gamma ray burst mission that we are working on at the moment. So I'm also presenting you. I wish you a very successful workshop, of course. I'm looking forward to watching some of the recordings. Okay.
Thank you very much.
For your meeting. Bye-bye.
Bye-bye. So while we wait for Rachel, I will mention her work as well. I hope she joins us later. So the next speaker is me. Sorry, I'm chairing my own session. I hope you don't mind. So I have to do the share screen. How do I do that? And then do this. Okay. And actually, I'll do the same thing as Harald did. The first time I'm here, closer to the microphone, and right. Okay, so I will do the kind of combined talk mentioning about the kind of connection between the ORP time domain and the Gaia alerts. I'm from Warsaw University, for those who don't know me yet, and I've been bombarding you with all those emails as well. So for this, okay, hope it works. No, it doesn't. Sorry. It works, but it's slow. Okay, fine. Right. So, but I'm not alone. This is the team in Warsaw. Most of the people from that team are here. You can recognize some faces, their names attached to them. Some people are online. They are actively involved in this as well. And then there is another part of the team which is located in Vilnius. It's really slow, this change of slides. It doesn't move. Łukasz. Łukasz. No, it's going to work now. No, it's fine. Because I have to have the active window where I click this. Now it works. Okay, these are the faces. Sorry, Ruta.
Yeah, I'm here. Yeah.
I didn't have your folder yet, so that's why we are just empty places. So these are the people involved from the Vilnius part. So we have the DINA grant, Polish-Lithuanian grant, working on some of those aspects together. And there is, of course, lots of universities and partners involved, especially Gaia, University of Cambridge, but other groups and universities as well. So what I'm going to tell you about is that why are we doing this? The motto, I think, which is relevant here, that there is always a time domain interesting object visible on the sky somewhere, right? And this is the map, a similar map was shown by Simon. This is a map of alerts from Gaia over some period of time. But there are also other surveys providing alerts, Assassin, ZDF, there's going to be LSST as well. So these are targets on the sky which are of scientific interest, right? And they change in time. And these are only alerts, but as I said earlier, there are also targets which are always there and are also interesting in terms of time domain observations, like eclipsing binaries, planetary transits, right? You can monitor the known boring variables, and then you can do very exciting science with that. So the time domain is something in astronomy what we've entered a few decades ago, but now it's kind of the time we are at the this is the very, very much developed aspect of astronomy. That's why it has a name, right? It didn't have a name before. If something has a name, it means it's real. So anyway, there is always somewhere on the sky, there is something of interest. So wherever your telescope is, whatever sensitivity you have, whether it's night or day, in your place, you can always point your telescope somewhere, and you're going to have something of scientific interest nearby. An example, a new type of FU Orioni time variable star found among the Gaia alerts. So you see the light curve from Gaia doing nothing for many, many years, and then suddenly slowly rising and getting brighter by few magnitudes. This is Gaia 18 DVY, and this was published in collaboration with, the work was led by the group in Hungary. There was supposed to be an example of a supernova, but you've seen one on Simon's slides and some others, and Laurent as well. So I'll skip that. There is an example, of course, of a microlensing event. You're going to hear more about microlensing events later during this workshop, because this is of our research interest as well. So there is an overlap. But this particular event is a perfect example of an alert from Gaia very early on a very bright star, and then a very intensive follow-up campaign, which provided a very dense time observations spread over tens of days, hundreds of days actually, and something what is essentially not possible with one telescope, not possible with one proposal, and thanks to this very dense coverage, we were able to detect the very high magnification of this event, and also thanks to the alert, we were able to do a lot of exciting stuff with this event. I'm not going to tell you more about this because Arnaud Cassin is going to tell about something we did with this event. So there is a lot of interesting potential interesting cases. There is of course many more microlensing events found by Gaia itself, and Katarzyna Kruszyńska is going to tell us more about this. That's a map from Gaia. Alerts, about 400 were found so far. Of course, we're looking for black holes. That's why the name of black hole, Tom, and so on. It's appearing here and there. This is the Holy Grail, let's say. But the time domain is the regime we are going to do. We plan to do this. These are the microlensing events found by Gaia. These are the light curves with Gaia observations. You see some of them, they have this characteristic shape of microlensing. Some of them are more crazy. But then some of them are, this is actually not finished yet, an example of not finished light curve. But what you see are the gaps in the data. This is Gaia alone. When Gaia observes something, provides Gaia, as Laurent nicely put it, Gaia is a variable star machine, right? So it provides time domain observations of the whole sky, right? But it's not a perfect machine, right? It has gaps in the data. And a striking example I'm going to show you, this is a microlensing event we alerted on, and with the alerts, you see there are gaps in the data, and kind of we found a model which fits the data, but thanks to the alert and then the observational campaign and some auxiliary data found in ZPF archive as well, we were able to see actually that the evolution of the light curve in multiple bands, as you see here, was way different from what we first suspected from Gaia data alone. That's why time domain observations from Gaia, they have to be supplemented with additional follow-up observations, right? This is to emphasize the need for follow-up. And this is a TOO kind of example, target of opportunity example. There is an alert, and we observe it, and we have some data, some information where to look and what to expect, but then we need to collect as much data as possible during the time. This is mostly the science case. So the thing is that without ground-based follow-up, we can miss the complexity of the event in that case, and hence we can miss the opportunity to recognize a black hole lens, right? So we are actually missing, we might be missing some serious science if we haven't had it organized. And there's going to be talk by Cornell, who will expand a little bit more on this. This is our observatory next to Warsaw. It's actually moving, as you see. And Monika Sitek here, she's not giving a talk about this, but I will mention it here. She's in charge of the forest. She's cutting the trees. She's oiling the telescope to operate it. She's replacing the CCD cameras and everything else. You can ask Monika about the details. But this is a small telescope from 1970s. It's a very robust machine, I must say, but still it's an old machine with a small mirror, 60 centimeter. So there's not much we can do with this telescope. And it's also next to Warsaw in Poland. Come on, who places telescopes in such locations, right? So it has very limited capabilities when it's on its own, right? So there's not much you can do because of the weather and the diameter. However, if you combine more telescopes of similar quality, right? I mean, they can deliver very nice photometric measurements because the mirror is size, Jena, it's very good quality. So the data itself is good, but we hardly ever get a chance to get this data, right? But if you have more telescopes like this, which are scattered around Europe and the world, essentially, then you lesser the effect of the weather, of impact of the weather, of the quality, then you can gather way more data. So we've established this network something like almost 10 years ago to support the forthcoming of Gaia alerts. Actually, before Gaia alerts started, we had this network already established, and now it's a network of about 100 telescopes. Some of them are more involved, some of them are less involved. But essentially, these are telescopes involved in a kind of voluntary way, and most of them are below 2 meters in diameter. And yeah, there's some animations you can recognize. Some of them. There is Ostrovik near Warsaw, but there's also Liverpool. There is REM. So we see some of them are robotic, completely, run with a click of a button. In some cases, and many of them are also manually operated by humans, and there is no chance you can actually think of robotization of them, but they are still useful. Each of them can be used. There is another example of a very nice science case we are currently very excited about. This is the Gaia 20 FNR object. It's a very long-term, bright southern object, and we have an idea. We see this is the data we've collected so far for essentially more than a year now. And sometimes the data there is tens of measurements per night. It's a very bright target, so it's fairly easy to observe with multiple instruments in the south. And that's why we are able to do some very exciting science about this. And in this case, we suspect that the lens, in this case, is a fast-rotating binary system, which we don't see, actually. We don't have to see the binary system to detect the lensing effect. So this is very crazy, and Chris Lewicki is doing a great job in finding the model while the event evolves. So we have quite a lot of data. That's going to be something nice. Then, of course, I've shown this many times, but this was the first example of what we can achieve with a network of telescopes. So Gaia 16 AYE, we used to call it Ayers Rock because of this mountain called Ayers Rock. Just to remember these names, these letters, but this mountain should not be called Ayers Rock anymore because it's Uluru. That's the proper name. Just to make it clear. So anyway, this was, as you see, this is also a microlensing event, but this was extremely complex. The light curve was exhibiting multiple peaks, and here you see data from 51 observatories, 20,000 data points. You see all the observatories listed down there. So we've been observing this for more than a year, almost 2 years, and eventually we found the model. Which otherwise, with Gaia data alone, we would not be able to find, because the Gaia data marked here in the red points would be just too sparse. There would be not enough information. So thanks to this very dense follow-up and involvement of many people, we were able to do science, right? So that's kind of the idea here. For this event, as mentioned by Laura already, but Chris Lewicki will tell you more about this. We are very excited because we can actually show you the very first time series of Gaia astrometry, not only Gaia photometry, as you see in the top panel of the slide, but also Gaia astrometry. This is 1D. I don't want to go into details, but Gaia gives you perfect, down to single milliarc seconds resolution of position, precision, the positional measurements of the source. And if you have microlensing, there's not only photometry changes, but there's also astrometric changes. So Chris was able to model this, and we've published this, published it as an image of the week. So this is the first time Gaia astrometric time series are being shown to the world. And we are very excited about this because this shows the prospects. Why are we doing this actually? Because for all those stars, 2 billion of stars Gaia observes, there will be astrometric time series eventually. They are there already. We've seen them, but we cannot show you them. Because this is still being processed. It's a very long-term, time-consuming process, and it will come eventually at some point around DR4. In a couple of years' time, not too long ago. That's a very nice visualization of this binary system. In this case, we also dealt with a lensing by binary system, not a black hole system, but we don't have to see any light from that lens. So it means we have a technique to detect binary black holes, right? Like the ones you see in gravitational waves, but way before they merge. So this is the technique, which is quite powerful. Okay, so now I'm going to the kind of the ORP part, what we do and how do we do that. So there is kind of a story I've been telling you already throughout the talk, but then this is more or less kind of a little bit better visualized way of this. So imagine there are surveys, right? So there are surveys like Gaia, and they provide alerts. There is ZTF, there is Master, there is Ogle, Assassin, whatever, you name it. They provide alerts, and especially with ZTF these days and LSST in near future, we'll see thousands or millions, people say, of alerts per day. So that's going to be a vast, we'll be overwhelmed by those. So people develop some kind of brokers, and these brokers are read by users, scientists. And scientists, for example, interested in microlensing events, they will use brokers to weed out all the supernovae, which are boring, and then just select interesting candidates for microlensing events, right? And then one user says, I hope it changes. Yeah. Please observe Gaia 20 FNR event for 1 year. I think it's a binary black hole. Please observe it for 1 year. Right? That's the science case this user wants to explore. Then there's another user who says it was a supernova in M881. Observe it now and throughout next few months, right? So what these users can do, this is what we are trying to do in the ORP. They go to us, so they send an observing requests, right? And they say exactly what they said in those plans there. And they sent it to this central coordination system, and we call it, in the grant application, we called it Time Domain Astronomy Central Coordination System, right? We also call it Black Hole Tom. I'll get to that in a second. So this is the central bit, and it's built upon Tom Target, an observation manager designed by Las Cumbres Observatory. I will tell you a little bit about it in a second, once I finish this story. So what this system does, it communicates with a network of telescopes, right? And as you see, there are professional telescopes there are professional radio telescopes there, but there are also smaller telescopes which are operated by schools, which are operated by amateurs. Amateurs these days, they have very nice telescopes in very nice places. So they can also join this. Essentially, everyone can join who has a telescope and is willing to observe something what is coming from our system. So these requests are then distributed over the network of telescopes, and these telescopes, they respond to them accordingly, right? So if there is no weather in Ostrovik, which is normally the case, Ostrovik is closed, but if there is weather in Lithuania, for example, they observe the target we've listed, and they generate data. And this data is coming back to the system. It's not going directly to the observer yet, because observers are normally not interested in raw data, right? Of course, there are very ambitious observers who are willing to work on their data, but there are also some researchers who don't have time for this, or they don't have enough postdocs or PhD students who can work on the data. And this is what we recognized as the major bottleneck of all the kind of scientific activities. It's easy to generate images throughout those requests, but then we're getting so much data. The data is getting left somewhere on disks and is never being processed because it's so difficult. It's generally not so difficult, but it's time consuming, and you have to know how to do this. So that's why this central coordination system is also tackling this problem, not only distributing requests to the telescopes, but also processing the data. So the data is coming back to the system, and what the system does, it prepares the science-ready data products, right? This is a very broad name. So far, these are mostly light curves. What I've been showing you the examples of, I mean mostly long-term photometric measurements, but we're not limiting ourselves to this only. This could be spectra, this could be radio images, this could be radio light curves, this could be polarimetric light curves, you name it. It could be astrometry as well. Whatever is possible to extract from the data is then being delivered to the users, and then the users, the scientists, they go and publish this, right? So you see, we kind of take over the burden between the communication between users and the telescopes, and we try to at least to simplify the communication here, so that the users, they can concentrate on the actual science work, and then have publications. So this is the black hole TOM, as it was designed. So this is the actual name of this central coordination system, and this is the website where it is. And the core of that system is TOM Toolkit, designed and built open source code and built by Las Cumbres Observatory. So Las Cumbres Observatory, and I hope Rachel will be able to tell you about this, but I will just briefly say that this is, they were actually pioneers in doing this. They have a network of telescopes around the globe, and they build the telescopes, and then they use the same CCDs, they process the data, they take requests from people. So they've been doing it actually for the last 20 years or so. So they are probably the best people we can learn from, and they were so great that they have designed a platform, kind of base code, which they provided for free to everyone, so we can expand it and adjust it to our needs. And I happened to visit them for a couple of months before the pandemic, and I attended a workshop so I could learn from them themselves how this works. And I thought this is just ideal for our case. So this is the main central engine, the code they provided. And what our black hole TOM system does, it communicates with multiple telescopes and it sends the observing requests. As you see, multiple telescopes are responding to the request. And these telescopes are generating FITS images, right? As I told you, so far we mostly concentrate on photometry. Those FITS images are then uploaded to the TOM, and the TOM is taking care of the photometry. It does the photometry with another brilliant piece of code being designed by people from Wrocław, and Sharon is going to tell you more about it in a couple of days. Then the photometry from those images is then being standardized, and this is where the Cambridge photometric calibration server comes in. And Pavel will tell you more about this in a couple of days. And then the data is coming back to the TOM. This is the product, the science-ready light curves. This is what we store at the very end, and this is what is available to users. And here are some snapshots from how the black hole TOM looks like. So you see the distribution on the sky of the targets of interest. There's a list of targets, of course. There's visibility plots. These are light curves. You see multiple observatories, multiple filters. You can upload your data through that. You can read the live curves through that. Everything can be done on this platform. As I said, we've done it with the help of LCO people, and then with a huge help from Akon Lab, a Polish company from Wrocław. And as I said, there will be talks about details, how it works. Maja Jaworska will do a friendly introduction tomorrow, and then Pavel will tell you about the calibrations, and then Przemek will tell you about the data processing. So that would be probably, I'm getting to the summary, but before getting there, I should mention something about the data, about the publication policy, which we are still kind of working on. That's why we have those workshops, to meet you and to talk about this. These are just headlines of some of the papers we've published so far. You see most of them are related to microlensing, but not all. You see there is a long list of co-authors, right? These are people who contributed to the data we collected, right? So this is generally the approach we are advocating. And in this case, we are processing the data, but we're also the users, right? We send the requests. So in that sense, we are in charge of everything. Our policy is that if someone provided data for the light curve, for example, then they are offered co-authorship of the paper. And that's why we have such a long list of co-authors. What else? Actually, in Black Hole Tom, there is a tab, publication, and if you click there, you can download a photometric table in the LaTeX form. It's essentially copy-pasted in your paper, and you have it. The next thing, we can download the statistics as well. One thing we still want to add is that with one click of a button, you get the list of co-authors you should include. So you don't have to worry, you don't have to contact everyone else. You just do 2 clicks, copy-paste it in your paper, and you're done. You have all the co-authors included, the table with the data, and with all the statistics, just ready for publications. So this is about the publication policy. So kind of in summary, I will say that the time domain astronomy central coordination system, i.e. the Black Hole Tom, it's a tool for scientists because it's a visual tool for long-term monitoring, 24 hours coverage, and it's essentially a global telescope organized in a very informal way. I know there have been many attempts of similar organizations, and I know they've been successful, but we do it our way, right? So for scientists, the message here is that we will observe your target, right? You just tell us which target to observe, how often, for how long, which filters. That's all we need to know, and then we'll observe it. We'll give you the data. And then for telescopes, and then for telescope users, for people who are thinking about building a telescope, or people who have a telescope and they would like to do something with it, then we will tell you which target is of interest for observing. So you use your telescope time, which is often limited due to weather. You use it in the most efficient way possible. We will also process your data, right? So you don't have to worry. You just send us the images, and then we'll take care of the rest. And this is another feature which is built into Tom. We can even operate your robotic telescope, right? So if you have a robotic telescope, we can plug it in, and then there's no human involved. The data is essentially being processed, the observations are being taken, and so on and so on. So that's the kind of offer we give in this Black Hole Tom. So there's a short list of new features coming soon. Scripted upload of data processing. Of course, you don't have to upload the data manually because you can script it and then connect it to your pipelines. So that is already in place. Automatization of observation triggering. This can be done with the robotic telescopes. Spectroscopic data processing. We already have the code, and Marco Lama is going to tell us about it in a couple of days, but this is not yet built into Black Hole Tom, but it is there. Microlensing model feed as well, it will come in. And what else we do, of course, within the ORP, we provide support and training to users, right? This workshop here is one of our activities in terms of providing support and training to users. We plan to expand to new telescopes, and if we have a telescope which is not yet in our network, we would like to have it, and we can, make a good use of it. The plan is to connect radio telescope, of course, as Hara mentioned, and then we would like to pilot the radio optical time domain observations, for example, quasar monitoring or transits. I will finish with the future. Time domain in next decade, right? There is going to be Vera Rubin Observatory providing, for example, alerts on microlensing, but then we will need a network of telescopes for that. So we are essentially learning now how to do it for the next decade. There's going to be astrometric data as well from Roman, WST, future Gaia missions. So this is mostly for the younger part of this audience. But this is how we are going to do it in next 10 years or so. And that's it. Let's stop here. Thank you. I'll now share my session. Questions, please. Vladimir.
I have two questions. One very simple. You show the picture with the white curve of micro lens and binary.
Yes.
What is the period of possible period?
Yeah, we know the period.
Mass.
We know everything. We have the period of about 2 years. We know the inclination, we know the eccentricity, we know the mass, about 0.3, 0.7 of components. Solar masses. So these are main sequence stars. Okay.
And second, this very nice observation and data you show, impressive. And my questions for future. You must divide transient to the slow, middle slow, and fast. Because if the amateurs will be observed fast transient, this amateur is professional.
Mm-hmm.
What do you think about dividing? What I understand that you're interested very slow.
Yes.
From my point of view.
Yes, they are slow.
True. Very slow.
Yes, so as I was saying earlier, is that the time regime here is not so urgent, right? We can cope with much faster, but the system is not designed for this. There are other systems for GRBs, for example, and people are doing a great job. In our system, it's a slow pace. Whenever you have target of interest, you put it in, then whenever you have time, you observe it. This dictates, this limits to some science cases, but we actually aim at long-term monitoring, right? Not that fast reactions. Our system has limitations, of course.
And one more question. I remember 20 years ago we started with our project. I tried to found the radio telescope for observation GRB. Prompt radio from GRB. Nobody observed. Why radio astronomers is so conservative?
Now
the possible flux is about 1 kilo Yansky. 1 kilo Yansky from radio. Of course, there is some questions with the absorption of radio in the, but we know this problem, but not excluded. Nobody sees. Maybe I miss something.
Well, I think that the amount of radio telescopes available is not so large, because you saw the European VLBI network is very
but we must prepare a new generation of small radio telescopes, like to very cheap system, about $15,000, because we have the very cheapest receiver and we have a very cheap antenna up to 12 meters for 1,000 Yansky now. Why nobody to observe? I found in Russia a lot of radio telescopes, but move very, very slowly and weightly, about 40 tons.
Yeah, exactly. And I think within the United States, the DSA 2000 array is being developed. And that is exactly something like that, but at a big scale. Yeah. But these dishes are only a few meters, and they have thousands of them, or at least they plan to have thousands of them. But that's a different target. They want to build images, instantaneous images. But yeah, I don't know, and maybe only now, for the last few years, that this technology to have small, lightweight telescopes that can move fast is sort of becoming available.
Can I ask you, to radio astronomer, the next questions? Another idea, if you take a very long wave radio telescope, like 2 interferometer, you know, that 1 kilometer length of electromagnetic wave, you can detect it binary neutron stars before merging. You can see, but you observe after merging, but you see this this effect before merging. Why? Because the velocity of the radio wave is very slowly, due to the intergalactic medium plasma. And for cosmological objects, this possibilities. You will see that published 30 years ago, but no people try to. I know in Ukraine, very long radio antenna near the heart. I don't know if you know this now problem with connect with this telescope.
But actually, it is still being active. And I think there's at least 3 now, UTR 2, 3, and there's another one being built, another extension.
You understand time machine effect.
Yeah.
Because high frequency comes very quickly, but low frequency tomorrow, but you can see binary before. That's very important problem. But before medicine is very interesting.
Can I cut the discussion here? Sorry. This is a very interesting topic, and that's why we have people from various domains here to discuss like this. I hope we can continue later. And there were some questions to me, but I think we have to move on. I'm happy to chat about this more on the Slack channel, possibly. And I see that Rachel Street she's now online. So Rachel, if you could now share your screen, and I've been advertising Tom in Vital, but I'm sure you'll do it much better.
Thanks very much, Łukasz. Let me just share the screen here.
Right, we see your screen, we see your slide, we can hear you. So Rachel Street from Las Cumbres Observatory, please.
Okay, thank you, Łukasz. And hello, everybody, and thanks very much for giving me this opportunity to speak. I'd like to talk about the experience of following up real-time survey alerts and some of the challenges involved, and give an update on some of the tools available to make this process more productive, which I see that Łukasz has already given a great introduction to. As you know, that modern astrophysics has entered an era where we have a wealth of targets. The Gaia mission has been groundbreaking in providing real-time alerts of discoveries on a wide range of targets. In addition to that, a wide range of surveys are in operation at all wavelengths and all messengers now, generating vast catalogues of discoveries. Advances in data processing mean that survey has also issue alerts of real discoveries in real time, and the rate of alerts is expected to increase by an order of magnitude over the next few years, especially as Rubin Observatory comes into operation. That facility alone is expected to produce 10 million alerts a night. So improvements in survey technologies have, of course, opened up vast new areas of parameter space to us, and astrophysics is now discovering phenomena such as kilonovae, and confirming the existence of phenomena that were predicted but very hard to detect, such as gravitational waves. Massive object catalogues, such as the Gaia data releases, give us extensive time series data, and these enable us to understand the evolution and movements of different catalogues of objects by studying their population distributions. So this wealth of discoveries means that researchers from all branches of astrophysics are facing the same challenges of searching this huge haystack of data for the needle of those targets that they are particularly interested in, and collating all relevant data on those targets. Now, if the targets are static or relatively slow changing, this can be a very labor-intensive task. But for those targets which are moving or change in any way, the challenges are compounded by the need to react quickly in order to obtain all of the necessary data while the target can still be observed. Furthermore, for many areas of science, the survey discovery alone, the data alone isn't enough, and additional follow-up observations are needed to characterize each target. For example, confirming the discovery of a single transiting exoplanet system needs data from several facilities. You need time series data in multiple filters to constrain the planet's radius, and which can come from a 1 to 2 meter class telescope. But the high resolution shell spectra needed to measure the mass requires a larger aperture telescope. AO imaging is likely to require an 8 to 10 meter class. And all of this is all for one target when there are catalogues of thousands of such objects to study. And the same is true for many other kinds of science. So it's clear that following up survey discoveries is a substantial workload by itself, as Łukasz just explained. And with modern surveys scaling up the productions to millions of real-time discoveries per night, we need to upgrade the technologies that we're using for follow-up to match the capabilities of the new surveys. So the requirements for real-time follow-up are technically quite demanding, and particularly for transient phenomena where all observations have to be acquired on a tight timescale. First of all, we need rapid access to survey discoveries. Now, the Gaia alert system has proven this can be done for a space mission, and a number of alert brokers now exist to aggregate information on new discoveries, serve that data publicly, and often provide classification information as well. At that point, astronomers need to identify targets that they are particularly interested in. And in most cases, they're going to have more potential targets, more candidates than they could possibly follow up. So some kind of prioritization has to happen. Having decided what they want to observe, then it's important for those observations to be made on a timescale that's dictated by the nature of the target, rather than at the convenience of a telescope's time allocation committee. So flexibility and responsiveness in telescope scheduling are essential. The results from those observations then often determine what the astronomer is going to do next. For example, if you get an initial spectrum of an object and find out that it was misclassified, then it may no longer be of interest to you and no further observations are needed. So having rapid access to the observational data products as well as the reduced data products is therefore very important to make sure follow-up is as efficient as possible. So I'm going to talk primarily about the technologies for these last three stages. So what observatory infrastructure is needed to meet these requirements? Of course, we have to consider the workload on observatory staff as well as the cost of implementation. And to that end, The minimum essential infrastructure is the adoption of dynamic queue scheduling, ideally supported by software to make it easier on the observatory staff, combined with making telescopes programmatically accessible so that users can submit observation requests from their computer instead of manually or remotely trying to operate the facility. The Astronomical Events Observatories Network, or AON, is a collaboration between the operators of Las Cumbres Observatory, SOAR, Gemini, and the Noir Lab to make the telescope facilities available to users in this highly flexible and very responsive manner. The requirements for partners in this network are deliberately kept as simple as possible. Firstly, the facility has to accept requests from observations through an online interface, which needs to have both human interface and a programmatic one. Secondly, the telescope has to operate in queue scheduled mode for at least some of the time. This can be achieved by fully robotic operations, such as for Las Cumbres, but it doesn't have to be. The SOAR telescope, for example, is still run by a team of human operators. AON partner facilities are welcome to use their own software infrastructure to meet these requirements. So, for example, Gemini has tools existing for users to request observations. So they just added a module to the TOM toolkit that allowed that tool to interface with their system. However, not all observatories have these software tools, so AON offers an alternative option as well. Partners can make use of the software that's developed by Las Cumbres Observatory to provide these tools, and that option was adopted by the SOAR telescope. The more telescopes that can offer flexible queue scheduling and rapid response observations, the better it will be for follow-up observers who are trying to characterize survey discoveries. So to that end, AON very much welcomes new partner facilities, and we are pleased to be working with a number of facilities as they become AON compatible. In particular, the facilities at the South African Astronomical Observatory and the 1.4 meter Milankovitch telescope in Serbia. Of course, developing an entire observatory control system software stack from scratch is a major effort, and telescope scheduling software in particular is very challenging. Las Cumbres recently released the full software stack of our observatory control system that we've developed to run the whole network as an open source package. And I want to stress that this is designed to be installed at any optical observatory so that it can operate entirely independently. There's no requirement to network with any other facilities. This is totally standalone. The package includes an online portal, which you can see demonstrated in the little movie there. And this allows users to request observations, and then it includes the LCO's adaptive scheduling software, which will then take those set of requests and turn them into a sequence that can be run at the telescope. The package also includes a science archive database and a portal so that the data products from the telescope can be accessed easily. And all elements of this software can be accessed programmatically, which really facilitates the rapid, streamlined follow-up programs. But having responsive observatories is really only one part of the follow-up challenge. In order to make efficient use of those facilities to characterize survey discoveries, astronomers still have a huge workload to manage the constant stream of targets, the data, and the observing programs. So the TOM toolkit was designed to streamline the management of astronomical programs. It's an open source package developed and supported by LCO's professional software team, working in close collaboration with astronomers both at LCO and in the wider community. It's written in Python and based around the Django web framework so that the system can be accessed simply from a browser without requiring any further apps to be installed. And it's designed so that even a novice developer should be able to customize it to their own workflow. At the heart of a TOM system is a database, which is designed to store data on astronomical targets. This is customizable, and it allows users to add parameters that are of interest to their specific science. So, for example, modeling data. The package also provides a framework for overall project operations, such as managing user accounts. It's particularly important that the toolkit provide interfaces to a wide range of external services in astronomy, and this allows the user to collate data and alerts for their targets of interest in real time. Now, thanks to the powerful programmatic interfaces being provided by many alert brokers and data archives, it's increasingly possible for researchers to automatically receive notifications of new discoveries and gather the information they need via software. This can also speed up the workflow. So that means that the researchers can respond more effectively to new discoveries. Users can upload their own data products to the TOM as well. So these can be either raw or processed data associated with observation requests, or they can be standalone products such as those produced by modeling or analysis software. The toolkit provides built-in tools for data visualization and to allow users to inspect their data directly within the browser. These can be very, very interactive, and they include image display tools as well as interactive plots, which can be customized, as you can see in these examples here. Of course, one of the most powerful capabilities that a TOM offers is the ability to submit requests for additional observations directly to telescope facilities. This streamlines the follow-up of all kinds of astronomical targets and significantly reduces the workload of managing an observing program, especially if you have to involve multiple telescopes. So the toolkit includes a set of built-in modules that allow interfaces to other observing facilities and allows users to submit their observation requests, monitor their execution, and then harvest the resulting data products from telescope archives. In addition to the browser-based user interface that comes with the toolkit, I wanted to emphasize that most of its functionality can also be accessed programmatically. All of the modules include APIs that are designed to allow functions to be called directly from external user-developed software. And there are a range of scientific motivations for doing this. For example, it makes it possible for a data reduction pipeline to interface directly with the TOM and upload reduced data products as soon as they're available, thereby increasing the speed of analysis. This is a crucial element in enabling fully robotic project management, which not only reduces the workload on researchers, but also makes the project more efficient and able to react quickly. So that's particularly important for transient science. I'd like to touch on some of the new functionality that we've been adding to the toolkit lately. This has been developed in order to support multi-messenger astrophysics, but the highly interactive tools are likely to be useful for a wide range of science, so we're integrating them with the base toolkit to make them more widely accessible. Multi-messenger alerts present some distinct follow-up challenges, as the initial discovery data is often not very well localized, and the first task is to pinpoint the specific source of the signal, and to do so very quickly while any counterpart is still observable. So our team have been collaborating with Andy Howell to create this new user interface, as you can see on the screen. It's designed to help astronomers to collaborate to create a prioritized list of candidate targets within the discovery region, coordinate the observation requests to a number of different facilities, receive the resulting data back, and then reevaluate and eliminate candidates that are decided to be non-viable. We've been working to have this available as soon as possible, and certainly by the 04 gravitational wave detector run. This is all based on some new, more responsive JavaScript tools that were built using the Vue.js framework. And that's allowed the team to implement a number of reactive user interface elements, such as candidate tables that can be more easily sorted or searched on with a single click. So I hope I've given you an overview of some of the tools that are available to streamline the follow-up of survey discoveries and to enhance the science return for all areas of astronomy. Each of these tools is distinct and standalone, but it interfaces with the wider ecosystem of alert brokers, observatories, and data archives that give us the whole of the infrastructure that we really need to meet the challenges of new modern survey follow-up. So I will stop there. Thank you for your attention. And if you have any questions, I'll be happy to answer them.
Excellent. Thank you very much, Rachel. try to make it, sound real, hybrid meeting. So there is a way to clap real, as in real meetings. There is a question from Haro. Haro, would you like to ask this?
Yes, Rachel, nice talk, thank you. I was wondering, I did not hear the word VO or protocols. And I think that's in some of the areas that you illustrate, the virtual observatory protocols at least might do something for you.
Yes, and that is, I did not have time to include everything that I would have wanted to. So yes, indeed, the VO protocols are extremely relevant to us. And behind the scenes, they are on our development list to incorporate, especially because the Rubin Observatory, which is near and dear to what I work on, is definitely VO forward in its stance. So that is something that we intend to integrate.
Thank you.
Thank you.
And there is a question from David Buckley. Would you like to ask this, David?
Yeah, sure. Thanks, Rachel, for a nice talk. I was just wondering if there's any synergies with the AMON system for multi-messenger follow-up, whether it's going to be sort of meshing with that in some way?
Yes, there's a number of interfaces that we can try and develop. AMON is one of those, and we've certainly been in contact with the AMON system operators before. At the moment, we have not implemented that interface, but it's on our list.
Thanks.
I notice in that area of astronomy, there's a number of tools that are being developed for coordination at the community level. Treasure Map is the one that springs to mind, so there's a number of different community coordination interfaces that are kind of on the table, and it's a very rapidly developing ecosystem. So we're trying to keep pace with that, yeah.
And Ashish is asking, can you elaborate on the tool you developed with Andy? Yeah, I was also very interested about this for the gravitational waves.
Sure. Let me go back a little. This one. Yeah, as I say, this is, and I wish I had a little movie demonstrating how this works. It's designed to make the workflow a lot more streamlined and a lot faster. So the initial Tom Toolkit interface is primarily based around a view of a single target interface. And so when you log in, you click on a target, you get a target. But the problem for gravitational waves is, of course, you might have many potential candidates within the error banana. So what Andy was really wanting was a list of potential candidates, and then to be able to simply, with a single click, say, this candidate isn't viable, put it to the side, this one is viable, let's prioritize that. And do that very, very rapidly in an interface like this one that can be viewed through a browser by team members that could be around the world. And thereby make it much more quick to evaluate all of the different candidates, prioritize them as a team effort, and then get the coordination of the observing program going. And so, although it doesn't seem like much to change the user interface to make that more streamlined, in fact, it saves the team as a whole a great deal of time.
Great. Ashish says thanks. I don't see any more questions here. There is one from Nada, the last one.
So the follow-up on this question actually, with gravitational waves, but how do you find the targets? I mean, from where how do you input the targets which are potential candidates? Do you have a tool for this? I mean, because you need to search right in the distance, and basically the ZDF or any other, or Gaia or any other surveys have to first detect them. So how do you find the candidates?
I'm sorry, I can't hear the question very well. Could you repeat
Come forward,
that?
no, because you're far from the microphone.
Okay, sorry. So my question was, how do you find the targets for this? So how will you input the targets, the possible candidates?
You mean
Because
for the
you
multi-messenger specifically, or to a tool?
Yeah, for gravitational waves. Yes, yes. So I assume this is for searching the electromagnetic counterparts for gravitational waves.
So at the moment, it is pulling information from the various public brokers that are supplying those information. And there's GraceDB, there's a number of other brokers that are processing information on multi-messenger alerts. So the TOM includes a number of interfaces to alert brokers, which we're using to pull that information in. And this display basically collates the information coming from multiple sources.
Okay, thank you.
Well, now we have to wait for some gravitational wave triggers to use this. Okay, thank you very much, Rachel. Thanks for joining us here. And let's move on to our last talk today. Vladimir, can you share your screen? We'll see how it works. Vladimir Lipunov, who's master of the master.
Okay, that is my process. A lot of people from different universities, from Russia.
Wait, we don't see your slides.
Share the one
on Zoom. Go to Zoom.
Yeah, Zoom here.
You have it up. Yeah. More the green from here. Yes. And now you go back to your slides. Now we see that.
Fantastic. Yes.
And full screen and you're on. Yes.
Okay. And so I would like to thank you very much for the invitation to this conference. I was on the first conference, guy.
In 2010.
Yeah. And these people from Russia, from several universities from Russia and from Argentina, Canary Islands, very dangerous now situation. I recently received the special letter from the director of the Gran Canarian Telescope about the help to people from the La Palma. So you can something to do in this case. Okay, what is this? I have something. Okay. And from South Africa, I see the David Buckley, and this is our closers, our collaborators. Okay. Oh, Mamma Mia, what happened? Oops, I'm sorry. The work.
Yes, it works.
Yeah, that is our laboratory in Moscow, and you see some young people. I like to see a new generation from the 20 years, from the first level to the postgraduate. And the master system now occupied several continents. We have the 5 telescopes in the Russia from Far East region, Baikal, Lake, Ural, and Caucasus and Crimea. And 3 telescopes we have in Canarian Island, South Africa, and Argentina. All telescopes the same construction and same ideological and same photometric standard filters, all from zero. This not new, 10 years, most of this telescope worked 10 years in Russia ago. Okay, this is our small 40 centimeter twin telescope. This telescope has the 3 axes, not 2. This gives us possibility to publish several papers in the Nature, because all telescope has only 2 axes. This is wrong. position in optical transient astronomy. In fast transient, very important, moving parallel or, and the field of view, maximal field of view 8 square degrees, and each tube has 4 square degrees, and have polarizators and several filters standard. Okay. Between alerts, the telescope works without any man participation. He found the fully robotical. We have the fully robotical telescope, and now we have fully robotical, maybe more or less fully robotical net. Net is more complicated because a lot of data must be this new level of the project. And we discovered 10 types of the different astrophysical, 10 to 8. That's an old slide, but in 17 years we discovered, independent discovered the kilonova. And so you see the different astrophysical types, the anti-transients. Stars disappear 100 times less photon brightness. And you see the old big telescope, large telescope, observe our transient. Okay. And 6 years ago, maybe, Amon started, and I participated in some conference about alerts and so on. And we now have collaboration with 3 or 4 messenger, 5 messenger astronomy, neutrino, 3 detectors, neutrino, and from Europe, this Antares and Ice Cube, and Russian. Recently we included the Russian Vaksan neutrino telescope. And you see radio, not gravitational wave astronomy, that is a Virgo, LIGO, and of course gamma ray burst, that is the first our goal to construct very fast, very wide field telescope, optical telescope. And the last 5 years, maybe 4 years, we observed fast radio burst, but because there is no any alerts, fast alerts, we proposed new type of observation for us, this monitoring of the fast radio burst with the known coordinates. And I show at the end of my talk, I show first result of this synchronous observation, optical and radio burst. Synchronous with radio burst. That is a classical team 20 years ago. We come to the GCN, the best astronomer, how to say, unification of astronomer and world. There's a lot of discoveries. I hope that the people which constructed this site must be Nobel Prize, because due to this site we see the very first bright optical burst on the another edge of the universe. After the Akerlof and his co-authors, forgotten his family now, unfortunately, discovered the 8th magnitude optical transient at the another edge of our universe. So we understand that our universe is very small, very small. The most powerful telescope built in this century, no more telescope must be built, because we see horizon of the universe. And so, I mean optical, telescope. Of course, gravitational is very, very important. And you can see that we occupied this business in the fast follow-up transient. The red is master telescope, the blue is the sweep. You see that the time observation in second up to 1 minute, up to from 60 to 70, so. And you see we are leader of the UV observation, gamma ray bursts, optical observation, gamma ray bursts. As two results in gamma ray astronomy, you see the best light curve of the gamma ray optical, not after low, because some of this, almost all this curve beginning as the gamma ray burst is not direct. That is very nice light curve. Half of them is master curve, light curve, and we found the coordinate, universal coordinate, unificator. All this you see here, amplitude about the 10 magnitude, the time in magnitude 10, in time several orders. But you see in new coordinate all have the same form. That's fantastic. That means that if you take best smooth light curve, you receive uniform of gamma ray burst. Waitable, but observationally, nobody uses this system. That is a normalized to maximum flux in magnitude. That is normalized to the time trigger. Another in our results, that is discovery of the prompt optical polarization. When we receive small box of error box, all two tube parallel, and we have two polarization observation. And first, that is optical, and gamma ray burst will be continued up to the 200, 300 seconds. That is a synchronous. That is polarization. Okay. Oi, mamma mia. No. Okay. The another very important for us results the independent discovery of the kilonova. Well known now the first localization, first optical localization of the gravitational wave astronomy. That is very important. The people remember that gamma ray astronomers 20 years do not know where is the source of gamma ray burst, because no optical identification, no optical localization. But after 1-2 years after discovery gravitational wave astronomers knows where is the origin of the gravitational wave. I'm sorry. That is the 17th August of the 17th year. That is my birthday in my passport. So I think God read passport before give us some present, because really my day 1 month young. In any case, you see 2-3 gravitational interferometer discovered very big, about 100 square degrees. It's 1 year in 20th century needed 1 year observation without any identification and no reduction. But at the evening, after 10 hours, we have the exact coordinate. People physical people not understand what happened when the optical astronomer discovered the object. Because in this case, the error box decreased in 1 million times. 1 million times. Where if you see optical transient, the error box of gravitational waves of gamma ray, Fermi gamma telescope have 1 million square degrees more than the optical. That's very important. And you see that the first we have two type of optical telescopes. This wide field image of this galaxy. The first image is this galaxy after merging neutron star, but this limit not very big. You see this the image which we observed before. There's 4 square degrees optical camera, 15 magnitude, 15.5 magnitude, not very big, but who knows what really. I was theoretical, but now I am observer, and I not believe in this theoretical prediction. Okay, you see how we discovered this transient. You see that is our survey. That is our survey. That is error box. The green square, our field of view, 4 square degrees. You see that is the optical transient in the supernova. And you see that is the beginning of the, that is publishing, that is our observation of kilonova. Okay, before publishing. And so you see this galaxy and differences between this reference image, that is you see the unique image, and you see different between this kilonova. That is after several days, nights, we observe this object in the South Africa master and Argentinian master, and we compose the color image. That is big our image, and our telescope can be found new stars in very, very big region during the real time, during several minutes after imaging. You see this kilonova, this square, this. If you want, okay, maybe after, later I show you some sort of film which demonstrated our soft. That the soft is very important because we photometrical all the stars during 1 minute photometrically done, and we have a lot of database. We not move any image we not move. All 8 observatory, 8 very good servers works every night, every day. Okay, and after that, I'm sorry. Okay, this well-known picture from the NASA. Maybe next one, neutrino astronomy. The people say, why you use a telescope for the neutrino? Because neutrino is very long time needed. The quasar, a very big black hole. You pointing after several minutes. Why? We have about 5,000 pointing to neutrino alert last 5 years. From Antares, Ice Cube is smaller. Antares a lot, but all site people not give us possibility for publication. In any case, this you see 3 really neutrino detectors, and most important our result. This is our telescope. You see this interaction between Ice Cube and master. After the 46.7 after detection Ice Cube, our telescope in Crete, Tablida, Tavrida now being Greek, the Greek name of Tavrida. Tavrida, Master Tavrida, pointing and found very unpredicted image. I would like to show you. That is the Tavrida telescope, installed 5 years ago. That is our image, and this well-known blazar, and all our images from different telescopes. And you see by air this blazar after several minutes after detecting neutrino, 2 times decreased. This image after 2 hours, between this image 2 hours, but we observe the sky accuracy 50 sigma, not 50, no, very big. This you see, if you was amateur in the childhood, you understand that it's very 2 times brighter. That is blazar, that is reference stars. You see all stars there. That is very well known. That is the result 22 September of the 17 years. We do not know about this observation because all observation was robotic. But at that time we worked with the Kilanova. But after several years we published this result. And you see that that is for our observation, this blazar from 2006 up to 2017. You see this event neutrino detection. So the signal noise ratio 50. That is a fantastic result. But some people say this might be occasion, some occasion result. You see this 0.7 magnitude style. After 2 hours, that is our image after several minutes. That is the ASAS observation. That is our observation after 2 hours. You see, blazar come back to the initial state. That is most short correlation between neutrino and optical. We have some theory. Now I don't discuss this. I am sorry for my. That for me very interesting because I lose about 1 year at the 20 years ago trying to follow up observation in radio astronomy. And from other hand, we published it in 30 years ago before discovery. We predicted how fast radio bursts really during the merging of neutron stars. Before merging, 1 millisecond you can read in the astronomy astrophysics when I was theoretical. And so we very interested in this object, and we observed this especially object. I'm sorry. You see this result. That is a fast radio burst, very high accuracy, radio astronomical accuracy coordinates, this point. And we try to observe the quanta which comes from this point. And we see with 40 centimeter telescope, we see 22.5 magnitude photons from this region. But this may be some hydrogen area, star formation area in the Z galaxy. This Magellan telescope, Magellan maybe, I don't know. Okay, that is the background point, that is a point we now know here. We use new type of astronomical observation, 2 tube independently. We calculated number of the coincidence between 2 tubes. This only statistical result. And who was astronomer amateur astronomer in childhood that remember that if you want to see Cassini gap, how to say gap? Shape Cassini in Russian. Gap. Cassini gap, you must very long time, several minutes, to see in the telescope when the air linsa is occasionally stay in good situation, you see Cassini, but 90% never to see. So we found this two coincidences to you, like to this not interferometer, but some like this coincidence scheme in the nuclear physics. And this very interesting method. You see this our telescope. This new our telescope, 60 centimeter, and in the Baikal region. Now we tested this telescope because new diameter. Thank you very much. I'm sorry for my English.
Thank you very much. Thank you for leaving questions to Vladimir. See, Hasha, please.
Okay, I have two questions. One is, how do you find targets which are worth observing? Do you track brokers like gravitational waves or other surveys, and then follow up as possible once you get the trigger?
You know, almost all, in all cases, we receive first image from the gravitational wave earlier, only automatically. People not come to the computer.
Oh, okay.
No, all automated, so because we have 1,000 alert observation per year. That's my head is destroyed very quickly because I must think about it. And I am afraid the time when the SST come to astronomy because all astronomy is died. That is a kill astronomy because new bio-robot, you understand? Yes, must be understand 1 million running per night. Okay, I 10 years, 20 in Cambridge, I say you must have there is theorem if LSST discovery new object he want follow-up observation with telescope 10 times diameter more. You understand what I'm saying? No? If LSST discovered if you want to spectrum, usually physical spectrum with mean resolution, you need 10 times more. And we will see after several times what will happen in astronomy. In any case, some people in our country say, oh, 40 centimeter telescope not needed. No, needed because we have, the Pan-star is loose gravitational wave astronomy. Why? Because Pan-star stay in the one island. Our telescopes stay on the different place. And fortunately, the two big alerts was from black holes and from the neutron stars received in the south hemisphere. And very nice project, PTF and my colleagues very not see this. So I am fanatic of the global cooperation, and I like this method of astronomy.
Go ahead.
How did they achieve such fast response? 60 seconds for a target that's very quick.
You see, we have a lot of inside the first minutes. No, if you observe GRB, you must understand that the space satellite lose 20, 40 seconds in sun for reduction on the board. You understand?
Yes, yes. No.
So we lose about 10, 20 seconds, not more.
Yeah, so my question is how is the telescope constructed to achieve such fast response time?
Oh, very fast mount, big field. The a lot of people after the Swift era, beginning Swift era, a lot of people think, oh, why I constructed wide field telescope? Because Swift give several minutes, several volts. And that is a mistake, big mistake, because family have the fantastic like to gravitational wave. And last year we discovered in Fermi region several very important. At last, maybe in October, yes, I don't remember. Don't have no time. Every time I lose to the writing the grant proposal and reading the negative result.
Thank you very much. Thank you, Vladimir. Thank you all. We have Vasilis now with us here physically. Well, thanks for joining us. But so you came to close today's session, right?
Yeah, I mean, sorry, I wasn't. The plan was to be here the whole day, but there was some admin issues with the department. I'm very happy that we were able to make it. When Lucas was actually scheduling this, I was much less optimistic that we'd be able to have it. But hopefully things work very nicely and we have it here. I think there are some, on the practical issue, I think, well, the day after tomorrow we're going out to Skimakers, so we need to arrange possibly tomorrow how many of you are coming and maybe be sufficiently ready so that we are back on time. And then I sent a list of restaurants. I don't know
I think we posted it already on the wiki page.
And
yes.
if there are any questions or difficulties that you may have, please let me know and we'll make sure that we resolve it. Thanks again for coming.
Good. So I think we will do a round of applause to all the speakers today. So we have it recorded. Now I can stop. So thank you all on Zoom for joining, and we'll see you tomorrow with the same Zoom link, but a different YouTube link. Bye.
Bye. Well, they will have